Can you guys hear me okay? Good. Oops. That works. Okay. I think we're ready, except it's not time yet. So get some to eat.
Not you.
Just accidentally kicked my dog in the face. Sorry about that. All right. How's everybody doing? I got my apples. I don't know. Maybe I shouldn't eat on stream. Gonna wait like a few more minutes. 3 more minutes till 12, so. Trying to think of like a 2-minute. Oh, thank you. Like a 2-minute YouTube video that I can play while we're waiting. I've got it. You guys are gonna hate me for this. This is 10 hours, not 2 minutes. Lots of beans. Okay. So for that, I had a friend in high school who he got that song stuck in his head for like a week, and he just sang it to us all day long, and it was funny at first, but then it got really annoying. As you can imagine. All right. So I think I've probably chased everybody away at this point, but let's get started. I want to do, so last time we covered IEEE format. I want to see if I can do all three of the remaining floating point topics in one video. Types of error, floating point operations, and special values. And I think I can. And we'll just have to see. I guess step one is looking at what types of error there are. So this is what I had pulled up. Where was it? This. Round off errors in computer arithmetic. Okay. Well, okay. I guess there are two different issues here. Things we could talk about. There are ways that you can get floating point errors, round off error and truncation error, and then there are ways of measuring the error, and that's actually probably a better source for that is this document. Rounding error, floating point formats, relative error, and ULPs. ULPs being, I just forget what ULPs are. Units in the last place. And we could talk about both of those maybe. The stream is, so I have no idea how to do this. I forgot to check a box last time, or I didn't even know the box existed that gets Twitch to record the stream so that you could put it on YouTube. I would like to put it on YouTube. I think I checked that box this time, and hopefully Twitch will record it and then I'll transfer it to YouTube or whatever that process is. I haven't looked into it too much. I'm hoping that it will work when I'm done. So hopefully, yes, I can get it on YouTube. And then, well, I mean, the result anyway goes on YouTube, but okay. Okay, so there are two ways of measuring floating point error, and there are two types of error when you're doing numerical analysis algorithms. So let's see. Let's start writing here. Maybe over here. Types of error. And we have round off error. And we have truncation error. Those sort of sound like the same thing, but they're not. I'll explain what they are in a moment. But then we have measuring error. And you have ULPs, units in the last place, and what was the other one? Relative error. So those are some things we can cover. And I think actually we want to cover the actual operations that you do first. And show how it works that when you add a big number and a small number, it show all the steps and show exactly why it is that you lose precision in the last place when you do a large number and a small number. And actually, I think I want to open the video with this. That seems like the most pertinent to a game programmer to know that. This stuff is good to know, and I'm going to mention it, but not quite as important. Like this stuff right here, measuring error, that's what you need to know if you're developing these algorithms. But we're really only just using the algorithms, so I think I'm not sure they need to be talked about at all. But this guy right here, I think we do need to mention. Okay. And then special values. So I've been thinking about special values. I was actually lying awake last night thinking about it. It keeps me up at night, special values. And what I want to do is not talk about it so much in the Blackboard section of the video, but talk about it more in the code section, because it's the sort of thing that I mean, you can't really talk about it. You just have to show it. So, if I break this video into a Blackboard section and a code section, like I do with most of my videos, then the code section can be specifically about those special values and then showing what floating point operations are a bad idea. And there are really two major ones. So, okay. So just organizing this all in my head, I think I want to open this video with operations that you can do on floating points and how they work and why they give you errors. And then talk briefly about the types of error. And then go to the code section of the video and do the actual programming where we examine the special values that you can have with floating point numbers. So, and then what I really want to do today is get to the second video. I want to record 2 videos today, which is what I usually do. And the second video will be the first root finding technique, which is our actual numerical analysis technique, and not just learning how floating point numbers work. And root finding is super cool, so I hope we get to that today. I'm sure we will. Okay, so that was the first video. We will copy that and paste it. Where's copy? I can never find copy. Paste. In Windows, I switched from Windows a few months ago. And in Windows, it's like the second or third thing, but in Mac, it's buried down in the middle of the list. So I always look in the wrong place. So what are we doing now? I don't know. Operations. And get rid of all this crap. Okay. And open this. Yep, save that. Can I just clear? Clear. Good. All right. Floating point operations. So I'll try and give a crappy explanation. And this is how I usually do it. I refine my explanation as I go, and it gets a little better. And then like the 5th take, I actually record. So when you have 2 floating point numbers, we're going to call them F and G. And we want to add them together. Last video we talked about how F and G are stored. They are, so F is going to have some, what did we talk about? I just erased it. Here it is, B times 10 to the E. Yeah? Oops. That button doesn't do what I thought it would. Okay, so we do F plus G. F is going to be some B1 times 10 to the E1. It has a B1 and an E1 that define it. And then G is going to have a different B1, or it's going to be a B2 and E2. Again, the computer would do this in binary, so it would be base 2. But we're doing it in decimal, it's base 10. But the process is the same. So we're just going to think about decimal because it's a little bit easier for us. Actually, let me do multiplication first. Multiplication is a little more straightforward. F times G. So the way that, so again, the computer stores F as a significant part, that's B, and an exponent part, that's E. And that constitutes F entirely. So then when you write some code like this, you have float F and G. You have 2 floats defined. This is in C or C++. And then you say F asterisk G, okay, and assign that to, I don't know, something else. Then the hardware does this, has to split F into its components and split G into its components and then apply some kind of operation to get the result. Okay, and so it has to find another floating point number in this format, in the same format, that represents the result of this operation. And since multiplication is commutative, oh my god, this is so easy. It's going to be b1 times b2 times 10 to the e1 times 10 to the e2. So I just rearranged the terms. This is all multiplication, so I'm allowed to do that, right? I moved the b2 over here. So there's the b2 now, b1 and b2. So b1 and b2, I'm gonna set that equal to b3, and then I have the b3 part. Now with this 10 to the e1 times 10 to the e2, I have to do a little bit of power arithmetic. So that's e1 plus e2 up in the exponent. Yeah? So my result is, and then I'll say that this part right here, e1 plus e2 is equal to e3. So b3 is b1 times b2, and e3 is e1 plus e2, and then b3 times 10 to the e3 is f times g. So the hardware has to multiply these two numbers right here and add the two exponents, and then it's done the multiplication of the two floating point numbers. And the hardware does all this for you. It does it behind the scenes. It's really, simple and weird. And it's really fast when the hardware does it. But then, so that's the easy one. Multiplication is the easy one. What happens when you redo f plus g? Well, now we have b1 times 10 to the e1 plus b2 times 10 to the e2. And this isn't like straightforward anymore. We can't really do this addition right here because we don't have like terms. So now the hardware has to do some crazy thing, and I'll give you an example. I think I did a lot of this yesterday, so some of you, this is review, but we're going to do it again anyway. I'm going to make E1 really big and E2 really small. And we're going to see why addition can be tough with floating point numbers. So we have these different exponents. In order to add these two floating point numbers and get something back in this format, we have to make those exponents the same. So this guy right here, he is really 5 and then with 8 zeros on the end. 1, 2, 3, 4, 5, 6, 7, 8. 500 million. This guy right here, he's really 2, but then the decimal place gets shifted to the left 6 times. So 1, 2, 3, 4, 5, 6. All right. So if I want to make these powers similar, then I have to move this decimal place. So okay, so I want this, hold on. Now I have to think about how this works. I want this guy to be an 8. Okay. So if I want this guy to be an 8, then I have to say 2 times 10 to the 8, but then I just added a bunch of stuff to this. We'll take, let's say 14, so times 10 to the negative 14. Okay, and then I'm going to add these two guys together, and that will be 2 times 10 to the negative 14 times 10 to the 8. And now I have another significand that I can put right here. And I also have like terms. Okay, I'll write that down here. Is everybody following along here? The first explanation always makes absolutely no sense. Times 10 to the 8. So if you have any questions, that's fine. So we have two significands now. And we have like terms. Why did I write an equal there? It should have been a plus. Right. Thank you, B617. So now we can add, and we get 5 plus 2 times 10 to the negative 14. times 10 to the negative 8. I don't know. If you watch my videos, you know that I do that all the time. So, okay, now here's the problem. Here's where the problem comes in. We have 5 plus a really tiny number. But like we learned last video, the floating point, like a single precision floating point, can only hold 7 or 8 digits worth of a number. So we're going to have 5.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But of course we're going to cut it off here. 1, 2, 3, 4, 5, 6, 7. So this 2 is going to be completely gone. Gets its head cut off. Gets its tail cut off, I guess. So the result will be just 5 times 10 to the 8. So, whoa, hold on. Okay, someone just got confused. Probably be faster if I just... It's okay. Okay. So... Okay. Crap, where was I? Yeah, the 14th thing. Okay. So the problem is we wanted to add 2 floating point numbers, 5 times 10 to the negative 8 and 2 times 10 to the negative 6. And when we added them together, we just got 5 times 10 to the negative 8. We just got the first one. So in effect, what happens is we did f plus g, and that equaled g, even though g is not equal to 0. Normally, you know, in math, f plus g equals f implies that g has to be equal to 0, but with floating point numbers, that's not true. So that is this what happens right here. What happens right here? This is a round off error. That's round off error. Okay. I should order a mic stand. So you're hearing like this stuff right here? Or this? I'll try and not do this. And I'll see if I can order a mic stand. This mic actually has... Yeah, it has a mount for a mic stand on it, so I'll see if I can get a stand next time. I'll try and not forget that. Okay, so that's one thing to be aware of with floating point numbers. The next thing is, don't want to bother covering this. Subtraction. If you do f minus g, and f and g are very close to each other. So let's see. Yeah, let's find some examples here. I'm going to set f is going to be 1.2345678 9. Very creative. Very creative. And g is going to be 1.23456 If I subtract these two numbers, oh wait, 1, 2, 3, 4, 5, 6. Yeah, actually we're gonna cut it off right here. If I subtract these two numbers, one moment. One moment. I want to make sure I got this right. Yeah, talks about it right here. Yeah. Yeah, this is why I don't know if I want to cover subtraction. Okay, so what it's saying is, here's 1.01 minus 0.99. Assuming that we only have, what is it using? 3 digits of precision. Okay, so we're not using any actual floating point number that you can find on a computer. It's just like, suppose 3 digits of precision just to make things easier for us thinking about it. So we only have 3 digits, and 1.01 minus 0.99 should be 0.02. I'm sorry, what? Should be... I should actually read it. Okay, they're doing 10.1 minus 9.93. And they're doing the same thing as we did before, where they have to shift both numbers to be so that the exponent is the same. So that's the same thing we just did. Where was it? And when they do that, they get 1.01 minus 0.99, and both of them are times 10 to the 1. And then when they do that again, when they do the subtraction, they get 0.02 when the correct answer is 0.17. The correct answer, if you look at 10.1 minus 9.93, it should be 0.17, but they get 0.02. So that's a pretty big error. But then what they go on to say is that most floating point units have a guard digit. And what is a guard digit? So, a guard digit is inside the processor. The processor actually stores one extra digit of the floating point number, and when it's in binary, so it's really only one extra bit. But when it does the subtraction, it does it with the extra bit. And that drastically reduces the error. So it keeps a little bit of extra information. And when it does the subtraction and when it gives you the result, it gets rid of that extra information, but having it there during the operation makes the subtraction a lot more accurate. Okay. And because of that guard digit, problems with subtracting floating point numbers are actually very much reduced and not a terribly big deal, especially in game development where we don't really have any algorithms where you need to be worried. Like quadratic formula is, the hell's quadratic formula? B squared minus square root of, B plus or minus square root of 4ac minus b squared, something like that, over 2a. This part right here is called the determinant. And what if 4ac is about equal to b squared? Then you have subtraction of two numbers that are very close by to each other. And floating point doesn't handle that very well for the reason I said before. But when do we ever solve the quadratic formula in video games? Occasionally. But if we get a result that is slightly off, that's not a terribly big deal most of the time. So yeah, I don't think I want to spend any real estate on this. But we learned something, didn't we? All right. I'll just stick with addition and multiplication of floating point numbers and explain how they work. Okay, so where are we? So let's see. We've learned about round off error. Truncation error, let's learn about truncation error. The way I think I want to segue through this video is that we do some operations and we learn that they can have error. So we already learned what round off error is. We just did it. Thank you, b squared minus 4ac. You know, I just got out of the math program at UCLA and you would think that I know about all that stuff, but at UCLA you learn about isomorphisms and all of this stuff. What is this? Categories and homomorphisms and group theory and stuff. And they don't care about the quadratic formula at all. So I forgot it. Okay, where was I? So we learned about round-off error, and that's a pretty good time to talk about truncation error too, even though we're not going to run into truncation error for a few more videos, but I still think it's a really good opportunity to talk about it now. And what is truncation error? Okay, well, let's do this. Let's look at the reference. The reference, truncation error. This is saying something really similar to before. No. Index. I'm at a T. Truncation. Truncation error. 11. Here we go. So it's difficult to talk about truncation error without talking about Taylor polynomials, because truncation error happens when you truncate a Taylor polynomial. So quick explanation about Taylor polynomials. Here's an interesting fact. Sine of x is equal to x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th plus etc. How do I have this memorized and not the quadratic formula? Yeah. So if you have a graphing calculator lying around, which I don't, it's actually a really cool exercise to plug all of these, like first plug x. Actually, let's look at it. Sine x. It looks like this. Yeah? Kind of like that. Okay? And I'm going to use a term, first order approximation. X is a first order approximation of sine. And that means that I'm just using the first term of this series. First order, first term. So let's see what x looks like. Actually, I'll draw x kind of on top of the other thing. Here's x. Right? So you can see that for values close to the origin, there is like x is a pretty good approximation. As you get farther away, x kind of sucks. Like if you want to estimate sine at what is this? 3. This is pi. This is 3/2 pi. This right here is 3/2 pi. Then y equals x is a pretty crummy approximation because it'll give you something up here where the extra value is down there. But for a certain range of values, the first order approximation is pretty good. Let's add another term. X minus 1/3 x cubed. So I'm actually going to go to, I think Mac comes with some graphing software. What's it called? I forget. Grapher? Grapher! X minus 1/3 x cubed. It works! Alright, so that's what x minus 1/3 x cubed looks like. So I will, oh, come on. Yeah. So I will overlay that on top of our little drawing of sine, and it looked something like this. All right. So now you can see it's a little better of an approximation. I can probably draw lines to about here, and we can get a pretty good approximation of sine inside those lines. And now let's do another step, plus 1/5 x to the 5th. What? Oh my god. I forgot my factorials. Yeah, I totally forgot my factorials. Factorial, factorial, factorial. I guess I didn't remember it very well. Okay, and you can see as I continue, minus 1 to the 7 factorial x to the 7, as I continue, it starts looking more and more like a sine wave does. 1 over 9 factorial x to the 9th. It's... yeah. Add new equation, sine of x. There. Let's see if I can copy this equation. Duplicate. Okay. I'll show you the whole series. X. Crap. X minus 1/3 x cubed. Good idea. And the next approximation is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. All right, and one more. X minus 1 over 3 factorial x cubed. This is actually, I like this software. I'm going to use it more often. I was only vaguely aware that it existed at all until like a week ago. Okay, so let's see the whole progression. We start with the first order approximation. It just has one term of the series, that's y equals x. Here is a second order, actually there's a third order approximation because the second term is missing. That would be the x squared term. I'm just going to call it the second order approximation. It's all relative, really. So the second order approximation gets a little bit more complete. And then the third order approximation, and then the fourth order approximation. And you can see the sine wave kind of forming out of all of these until, if you extend that this series infinitely, 1 over 11 factorial, 1 over 13 factorial, etc., into infinity, you will eventually get a sine wave. So back to the question, what is truncation error? Truncation error is when we cut this series of polynomials off at some point. We say, okay, I have a pretty damn good approximation for the range that I want. Let's see. Within like negative 3.5 to positive 3.5, I have a really good approximation of sine. I don't need the rest of the terms of the series. And that's all of the, like you have from 0 to pi, you are so close to the actual value of sine that you don't need the rest of the terms. And you can, if you want something at 4 or 4.5, you can say, well, that's actually going to be the same as something near 1, just negative, because that's how sine works, right? So you can get around the fact that you don't have enough terms in your sequence in however many ways. And series like this are used in numerical analysis a lot. So that is truncation error. Truncation error is when you say, okay, this many terms in my sequence is enough, and I'm going to accept a little bit of error in order to calculate it faster. Obviously, 4 terms is faster to calculate than, infinity. I don't think that this is how the computer does it. I think the computer has tables, and they do some kind of clever interpolation, or not. Maybe I've never actually looked at what is the state of the art to calculate sine of x. This would get you. It's actually really common, especially if you ask a physicist, to use the. This is called a linear approximation, first order or linear approximation. To use the linear approximation if you know that you're very close to the origin. That happens a lot because it's a lot easier to calculate x than it is to calculate sine of x. But then you have this truncation error right here. Okay, so that's truncation error. So that's an interesting question. Do I want to even bother talking about truncation error in this video? Because I have to, you see how I have to talk about, well, first of all, are there any questions on that? I want to make sure I don't get too far ahead of anybody. And is it a good point right now to talk about truncation error when we might not get to this sort of stuff for a while? How pi is calculated is an interesting question. I don't actually know. I know that historically the first guy to calculate pi to any amount of precision did it by having a gigantic, I have no idea what the state of the art is. And like in C and C++, there's a constant m pi that you can just, queue up anytime you want to get the value of pi. And it's calculated for you. And there are mathematicians like calculating digits of pi, but, I think it's pretty boring. The very first guy to do it laid out, I think it was like 10 meters in radius or something like that, a huge circle on the floor, and then he surrounded it by some shape here like this, and another shape here like this. So he said that so the length around the dark blue circle is 2 pi, obviously. That's the circumference of a circle. And the light blue circle has to have, if you trace the 4 sides of the light blue circle, it has to be strictly less than the diameter, than the circumference of the circle. And the outer light blue circle has to be strictly greater. Does everyone see what I'm saying? If I take the, God, what is it called? Words. If I take the distance that you travel, if you go from, if you trace the outside of this light blue circle here, right here, that has to be bigger than pi. So I'll call this here's A and here's B. The circumference, I'm just going to say circumference because I forget the word. The circumference of the outer light blue circle has to be bigger than pi, and the circumference of the inner light blue circle has to be smaller than pi, right? So A is bigger than pi, which is bigger than B. And then let's make that more accurate. So he made an octagon, right? And then he can do it again here on the outside of this circle. He made another octagon. And you can calculate the circumference of a general polyhedron, not polyhedron, what is it? Polygon, perimeter. Thank you. My God, perimeter. Perimeter. I'm a math person, not an English person. You can calculate the perimeter of these purple polygons a lot easier than you can calculate the circumference of a circle. It's just some irrational number. So we know that A prime is bigger than pi, is bigger than, Actually, I think he didn't even calculate it. He just measured it or something like that. So he laid these huge polygons in a circle out on the floor, and then he just measured or did some calculations with it, and he figured out a pretty good approximation of pi that way. And I want to say it was some ancient Greek guy. It might have been like Euclid or something. Pythagoras, maybe. I don't remember. That's a cool story. Anyway, the state of the art for calculating pi, digits of pi is math that I don't think I would understand. Oh man. Let's see. Number file, of course. And yeah, of course he did a video for this. Well, I don't think Pythagoras or whoever used real pies, but it's that sort of idea. I'm not going to watch this whole video right now. Okay. You could use this formula to calculate pi pretty easily. You would have to use also what we're gonna cover in the next video. I don't have it here anymore, which is a little bit of root finding. But we'll learn about that later. I think I'm actually not going to cover truncation error in this video. Let me look at my list. My list of stuffs. Oh, come on, recent. So in what things that we're going to learn are we going to use truncation error? And actually we're not going to really use it until we get to Rungakutta. That's this guy. Yeah, okay, well, we learned it, but it's too crazy, and I have a budget. I try and keep each video under 10 minutes, which doesn't always work. I know I have a bunch of 14-minute videos, but I really have to cut stuff out because I can kind of go on about math, so that was cool, but let's not do that one this video. Let's not worry about truncation error. Okay, so the plan for this video so far: talk about multiplication of floating point numbers. Once we learn how that works, it's just the same thing as multiplication of scientific notation. Then we'll look at addition of floating point numbers and see how we can get some problems there where we lose information. And then that will give us an opportunity to talk about round-off error. So talk about round-off error for a minute. And then, what was the next thing we were going to do? What was the next thing we were going to do? I don't remember anymore. Special values. Special values is the code section of the video. All right, code section. So here we are. Getting rid of the stuff I was doing before here. Do I have a project for this? Yes, I do. I bought my dog a squeaky toy yesterday, and he freaking loves it. So if you hear squeaks, that's what that is. Sorry. If he goes too, too much off on it, then I'll take it away from him for now, but he freaking loves that toy. I really don't have a... Great. Do I have... So I promised somebody that I would explain my programming setup. How I code, and I will do that now. Oh, it's just a make file. Make. Build. And it doesn't build. Great. Why is it using Linux? It should be using OS X. Oh, because I have to use the OS X make file. Great. Okay, well, let's just explain my coding setup here. Or not, because this thing doesn't even build. So obviously I use Sublime. Let me make a new build system for Sublime real quick so that I can get this thing building on Mac. And then we can look at what am I doing here? What am I doing? Give me a new Finder. And Documents. And Git. And I don't know. This one. I'm rewriting my blog right now, so I happen to have this all handy. I copy that and throw it into, where is it? Throw it into here and then just say make -f makefile.osx. That still didn't work. Oh, because I have to make OSX. That still didn't work because I have to do this. And now it will work. Oh, what? Oh, I have to do this bullshit. I said a bad word. Okay. It builds. Oh, it was already built. Great. I feel better now. And actually, you know what? I'm gonna put this down for a second because I'm gonna go into my own like side crazy game project that I do in my spare time. It's called Grotto, and I'll show you my build environment from there because it more reflects like how I actually do C and C++ here, and it's all ready to go. So this is Sublime, obviously. It's amazing. I fell in love with it. And it has these build systems that you set up. I mean, they're kind of tough to get them going. You have to do all this like crazy JSON stuff. But I have one that says build Grotto, and it executes a shell file. And let's open up that shell file, build OSX. And it is literally a shell file that builds my project. I don't use makefiles. The idea that you can use something other than makefiles to build your stuff I got from, you know, Casey and John Blow and all these people. And I really like it. I have some tools that it helps me build. I mean, it's kind of an involved process to build it, but it's really just a simple shell script. If you know shell scripts or bash scripts, they're not hard to put together, and it gives you a lot more control. It's easier to the syntax for makefiles is kind of difficult, but I understand shell scripts a lot better. So when I do Command B, it builds it. There you go. It's built. I can blow away the directory that it puts all the build files in so that you can see the whole build process. It builds Igor, which is like a utility that helps me read all the assets and assemble a list of assets. And then it builds Grotto, which is the game, the actual game. And then done. It's actually like I'm in the very beginning stages yet, so I can't show you like it doesn't display anything when you run it, but we're gonna run it anyway and see what happens. This is my debugger, LLDB, and I'll give you a short run through of how it works. It's a command line debugger, which I don't really recommend for beginners. Command line debuggers are difficult to get into, but since I've been doing this for a while, I'll explain everything I do as I type. bmain creates a breakpoint in the main function. I like a shell script option over a makefile. It's easier to also package a binary afterwards. Totally. Yeah, and you can have a few different, like I have a shell script file that runs all my unit tests. I can switch to it real quick. Run tests. Let's run my tests. All tests pass. I don't know if you can see it says that right here. So it's a lot easier to do that than do a different make target, and I don't even know how make targets work, and it's confusing. So I put a breakpoint in the main function. Main function, of course, is the function that it runs when you run the program. I'll press R to run the program. And, oh wow, I guess there are a lot of functions called main, huh? Okay, well, it added breakpoints to all the main functions right there. So now I'm stepping through my program. I can press N to go to the next line. And it shows you a little bit of context for each line. And since I'm on Apple, it has to do a bunch of junk. You can just keep pressing enter. You don't have to press N, enter again. You can just, oh, it loaded up the window. You can just press N and then keep pressing enter, and it'll continue to take you to the next line. S to step into a function. And then fin means finish, to step out of a function. If I want to, like if, actually that would have been a good place to do it. So sometimes you get stuck in a loop. This is some crazy loop that's playing. And I just want to, it was a short loop. Sometimes there are like 1,000 things in the loop and you don't want to be pressing N. I just want to go like to the end of the loop. So this is the equivalent of, I think, Alt F10 in Visual Studio. I just want to run until a certain line that's outside of the loop. I can say thread until, and then give it a line number 32. And it'll just take me right to, it will run the program until I get to line 32. And you can do that the short way, thread until 32. For most commands in the command line debugger, you can actually just abbreviate them, and thread is just th, and until is unt. So get out of there. What else do we need to know? Oh, so what are all my local variables that are sitting in my current stack frame? The command frame v will show them. And I have a bunch of stuff. There it is. If I want to print an individual one, I can say print input. And these are all the input parameters. If I want to print out some memory, I can say X, and then let's see what's at this memory location. Last slash is, what was last slash? This is all runtime. This is the debugger, so this is all happening while the program is running. Yeah. It's already been compiled, and I'm stepping through each line of my program and seeing what it does one line at a time. So where was I? Oh yeah. So last slash is just the first argument. So let me do x args 0. So I'm printing out the memory at the location args 0. And the first argument is always the name of the binary that got run. So it's giving me every, 75 apparently maps to the letter U. It's giving me the value at each address in memory, and then on the right it gives me the string representation because that's handy. Now, will it display images for me and play sound buffers and that sort of thing? No. But Visual Studio doesn't do that either. So, and then if I want a ton of it, if I have, it gives you, what, 32 bytes by default? If I want a bunch, I can say -C 1024 bytes, and it'll give me a ton. It'll give me, 1024 bytes of whatever is at that memory address. So that's useful. Setting breakpoints, I showed you bmain. You can also do b and then give it a file name, main.cpp line 40. So I have 2 breakpoints now. What? Oh, breakpoint list. There we go. I have a bunch of other breakpoints because everything called main got a breakpoint on it. Okay. But then I can, so I used the wrong command. I said blist. B is like a special shortcut. If you want to actually maintain your breakpoints, you have to say brlist. And then I want to delete breakpoint 3 because I accidentally made a breakpoint at every command called list. So I'm going to delete that breakpoint. Anyway, so it's gone. So I have 2 breakpoints now. One is in main line 15 and one is in main line 40. So if I run the program again, I break at line 15, and then I press C to continue execution until I hit the next breakpoint, which was at line 40. There it is. So you can do break list, break delete. If you just press break delete without any parameters, it deletes all breakpoints. Let's get a little deeper in the call stack so I can show you this guy. BT gives you the backtrace. It's a stack trace, same thing as you get in the stack tab in Visual Studio. And I have 5 frames on my stack trace right now, and I can go immediately to one, like I'm in the highest one, I'm in a free binary procedure. I can go to the lowest one by saying F3 and I'm back to the main function. The actual execution of the program is still up in free binary, but now I'm examining things that go on in main. So if I do frame V, it gives me the locals for main, but if I go back up to free binary and do frame V, it gives me the locals for free binary, which is just, there's only one local. It's called binary. So that's the stack trace. What else do people usually do when they use debuggers? I don't use data breakpoints really ever all that much, so I don't know how to do that. Wait, I think I made a note of this at one point. A note. Ah, the cheat sheet when I was just learning how to do it. Yeah, and okay, we covered all this. So that's my debugger. It's maybe a little bit scary to new people who haven't done a lot of debugging or a lot of C or C++ before. If you want to go tails in, or what is it, head face first in, whatever that expression is, then you can try this. And the reason I do this instead of like Eclipse or something is because it absolutely, positively, never freezes up. Ever. Well, okay, wait, that's not true. It did freeze up once when I smashed my stack. And so like the stack trace got, well, I don't know if I want to explain that right now. Smashing my stack. I wrote over where the stack in memory was. I wrote, like, accidentally, I wrote some bogus information in there. And so when you do this BT command, it has to walk back through the stack. And since I wrote some crap in there accidentally, it couldn't do that. And it froze up when I did that. And that was my fault. Other than that, it's never frozen up on me, whereas Visual Studio just seems to get worse and worse. Like, now you have to log into it. Why do I have to log into my text editor? I don't know. All right. Where were we? Okay, so that's my environment. And Sublime has some really nice stuff like Control D, which lets you edit, like have multiple cursors and stuff, and I don't know. None of that is relevant to what we're doing. So let's go back to the math project. We're here to do math, right? Math is good. Let's go back to math. So I have a main file. Main, where is it? Wait, is it called main? Where's my main file? Seriously? No, here it is. Main. Okay. So we're gonna do the same thing basically, and let's get rid of this video or window. We don't need it anymore. Kill this debugger. Math for game developers. Yeah, my pleasure, man. I actually have a nice shell script that does it for me. Yeah. Yeah. Oh, it crashed. Why did it crash? Memory read failed. Let's get a backtrace. Oh yeah, so if you hit a bug, the debugger says bad access. You know, it stopped for this reason, bad access. If it were one of your breakpoints, it would just say breakpoint here. But so I made a bad access. It looks like I was trying to bind a texture. And what texture was I trying to bind? I don't know what this is. And I don't want to deal with this right now. But we don't have to, because we're not going to use any of this stuff. So I'm just going to return 0. Like, I'm going to have to figure that out for some of the next videos, but I don't want to deal with that right now. So let's just see floating point numbers at work. 1.0. Let's do this. 1000. Float b equals, and let's see what is the, okay, wait, float c equals a plus b. Let's see what is the limit at which, like, what is the most amount of precision that I can get from from floating point numbers. When will it cut me off? Is this too much of a difference between a big number and a small number or not? Let's see. So we're going to print the result here. F C. Good. Build that. That's not what it's supposed to say. No rule to make target. Oh, yeah. So I actually have a Windows laptop lying around here somewhere, and I'm gonna just port it to PC, my game, when I'm done with it. But for now, I really enjoy the Mac interface. I like the touchpad. I know, like, John Blow and Casey Muratori hate the touchpad, but I think they're very nice people, but I don't like the touchpad. I like the touchpad. And the general, like, Mac, I feel like, puts more thought into their interface, and it's just easier to do things. And so, I don't know. I became a Mac person. I was a Windows person for, my entire life until about a year ago, and I decided to get a Mac, and I really like it. It doesn't freeze up nearly as often, and, like, it doesn't have all these crazy... So I develop on the Mac, but of course I'll ship the game on a PC. People kind of look at me weird when they say, wait, you're a game developer and you have a Mac? What? Why? What? So, I'm a dancing shadow zombie. What was I doing? Okay, I'm not even bother with that makefile right now. I don't want to mess with it. Let's see if this will work. Yeah, that worked. Why didn't it work here then? Did I not? Did I tell it the wrong thing? Did I make it mad? That's not what I want. I want this. Make -f makefile.osx. Make. I don't know. I don't know what's doing that. And I don't care. Alright, so we're going to load up the debugger. We're going to put a breakpoint at main. We're going to press run. Here we are. And optimizations are on. That's not what we want. Makefile and O2. We're going to comment that out. Save it. I like Mac too. It's the same as more popular gaming environment. And also, like, Apple doesn't care about games. Like, Microsoft these days, they're shooting themselves in the foot. But, like, back in the day when Windows was rising in popularity, they cared a lot about games. And I don't know, somebody was smart at Microsoft and they realized that if you can get games onto this platform, then it helps sell the platform. Mac is targeting a different audience. They don't support their OpenGL drivers very well, and and they don't really put a lot of effort into supporting developers to make games on their platforms. And that, I think, it's not just the momentum of Microsoft that's part of it, but it's also that Apple really doesn't care about games on their platforms, which is sad. I use Unix as my daily driver. I use Windows for games, but Linux for real work. I've gotten so used, yeah. That's why I like a Mac, because I can get the command line here. I have all the GNU stuff and Bash. But then, like, I don't have to put up with... What is that new thing that they... Oh, it's not new anymore, but the new window thing that they have that everybody hates, that Ubuntu did. I don't remember what it's... Oh, Unity. Like, I don't have to put up with that, and like, none of them are really good, to be honest. Like, Unity is the worst, obviously, but the KDE and GNU, what is it, GNU Desktop or stuff, and that sort of thing, they're not really that great. They're serviceable, but I've never used PowerShell. I don't know. PowerShell's Windows, isn't it? Yeah. Oh yeah, no. Yeah, it's like... Whatever. And you know what? Use what you like. It doesn't really matter. I like Mac. It's not like I'm not a better game programmer because I use Mac. You know, I just use what has the least friction for me, and that's what works for me. So okay, what am I doing here? Let's clean. I don't want you guys to start using a Mac just because I'm using a Mac. It doesn't, it's pretty arbitrary. My wife uses Linux. She loves Linux and does everything she wants her to do until one of her office mates wants to send her a Word document, and then she gets frustrated with the world. So hopefully that turned optimizations off. Set a breakpoint in main, run the program. Good, optimizations are off. I knew optimizations were on, by the way, because notice how, where was it? Notice how I started the program, I ran the program, and then it put me directly to the printf line, and it skipped all the other lines. And it did that because the compiler had optimizations on, and it did something called constant folding, which, like, if you look at our code, this is a constant. Like, I'm assigning it to a variable, but it's a constant, and so it just propagated that value down, and it got rid of all of these lines. It got rid of them because, like, every time you run the program, those 3 lines are going to turn out the same way, so the compiler's like, throw them out. So I could tell when it hit printf that it had done that. So, but now it's not doing it. Okay, float A, float B, float C. So if I do frame V, we can see that, ooh, look at that. That's interesting. Instead of 0.0001, like I thought I assigned this variable, it has given me 0.00009999974. The reason for that is that the floating point format is in base 2, and you can't specify some numbers perfectly in base 2. Like, we think in base 10, usually. Most people do. We have 10 fingers. But the computer thinks in base 2, and if you can't fit that 0.0001, yeah, that's what it is. Well, it's not. It's kind of a combination precision problem and base 2 problem. The computer's using a different base than us. But 0.00009 repeating is close enough to 0.0001 that, as game developers, we won't care. If we were doing scientific computation, we might care about that and use a double or something. Let's see what happens with doubles. This is why Sublime is cool, by the way. Control D and bam. Now I'm using doubles. Oh, I have to do this now. Good. It's actually rebuilding it. And then B main, run it. And now we see we have perfect precision on the double. And adding the two together works. Yes, it does. Same thing happens. If we could think in base 2, then, and as programmers, kind of we do start thinking in base 2 sometimes, but I don't know. I still think about floating point numbers in base 10, honestly. Okay, so back where we were. We see that when we add these two, so this is actually weird. We added 1,000 and 0.0001. B, the floating point number B got rounded down from 0.0001 to 0.00009. That's less. But when it gets added to C, what? It's actually bigger. So it's like, what is this? The wrong file. This. Yeah. So we have F plus G. Let me do this. The problem here is we have this function that takes an arbitrary real number to a floating point number. So in math talk, it takes an arbitrary real number to a floating point number. Okay? If you don't recognize this notation, that's fine. F, give it a real number. Let's say A. A is any real number you can think of, pi, whatever. And it gives you x, which is in the floating point format. Okay? So this f function is what the compiler is doing when I type 0.0001 and I get something different. It's because it passed it through this f function, okay? And in fact, let me call it FL. That's what my textbook calls it. So the compiler is changing it kind of under our noses, and most of the time that change is just innocuous and okay. But we can see it does not commute. That's a very good question. And it does not commute. Wait, is that true? No, it does commute. That is a good question, and let's look at the addition part. Like, all of the operations that we did here are commutative operations, so I don't really feel like... It doesn't associate, though. It's non-associative. So if you have a plus b plus c equals a plus b plus c, I'm going to put some parentheses here, I'm going to put some parentheses there. So we saw that sometimes f plus g equals f, right? So, so we could have, like, if a plus b equals a, then this comes out to a plus c, but the result of b plus c is going to be different. So when you add, okay, maybe use a different apple. This is my lunch. Big plus small plus big. That's what I'm going to do. If I put the parentheses here, how do I make this work? Oh my god. Small plus big plus big. That should do it. All right. If this is like our F and this is our G, then when we add the two together, I'm pretty sure it does commute, now that I think about it. I just get F, which is the same big number as before. And now we get big plus big. Let me do it this way. Or I'll do this. Plus negative big. Big plus negative big equals 0. Okay. But if I put the parentheses in the opposite place, plus negative big, here, okay, now big plus negative big equals 0, and you get small plus 0 equals small. So you get a different result depending on where you put the parentheses. I hope that made sense. And that is an excellent point, and we should cover that in the video. Thank you for reminding me. Let's actually see that at work. Where we finished here? Oh yeah, I went to the blackboard to show that the, like, B is, so we have our floating point function, and we put b in it, okay? And that is smaller than the actual b. But when we add floating point a, which is equal to a, plus floating point b, that is bigger than a plus b. What? That's just how it works sometimes. If we were to examine all the actual steps that the processor used, we would see why that happens, but I don't really think that's important. So let's add a 0 here. Come on. What's going on? Okay. I actually want to get this working. It would be a lot more convenient if I get this working. Oh, I know why it's doing that. I know exactly why it's doing that. Oh, do I want to bother with this right now? Okay. Give me one moment, and if it takes too long for me to figure it out, then we'll just go back. But I think I've already solved this problem in Grotto. So, yes, yes, yes. No. Yes, 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 yes. Okay, yes, it worked. All right. So now we have it building when I press Command B, so we can just come back here and rerun it with the R command. And there we go. It gives us the new program, so that's a little bit less hassle. Good. So, okay, great. Now we see what we were looking at before, where we added A and B together, and B is too small, and then A got shifted out. I'm sorry, B got shifted out when we added the two together. So we add them together, and you see it gives us, the output is just 1,000. Those are those 8 digits of precision that we were talking about, because we should get this number, but that would be 1, 2, 3, 4, 5, 6, 7, 8. Those are 8 digits already. We've used them up. And so when we add that extra 1, it don't work. Okay, so now we're going to try a plus b plus c. So let's make a c that is negative 1,000. Let's say negative 999.9. 99999. And then d1 will be a plus b plus c. And d2 will be a plus b plus c. Did I put the b in the right place? I didn't. That will work. Run it. A, B, and C. Let's see what they are. Frame V gives us A. A got screwed up again. Oh, it rounded C up. It rounded C to negative 1,000, even though we typed a lot of 9s. So let's remove 1 or 2 9s. Again, that's that floating point function that... and again, with video games, like, you don't really need that much precision. I think you really need like 6 or 7 digits, but that's it. So if we're talking in meters, millimeters, like here's a meter in your game. A millimeter is like, I can barely hold my finger that small. And that's 3 digits of precision. So 6 digits of precision is a micrometer. To do physics simulations, that's all you need. So this time it kept our negative 999. Of course, it changed the last few digits, but that's fine. So let's see what D1 is. D1 is almost 0, but not quite. Let's see what D2 is. A completely different value. And notice where it screws up. It screws up in the 3rd digit. So that's kind of important. Like if it screwed up here, like when it screws up here at the end, we gave it, how many 9s did we give it? 6 9s. And it got all 6 9s, but then it added a very small amount in the very farthest bit of precision. And that's like, you know, whatever. Only the last few digits are wrong. We can deal with that. But if the third digit is wrong, that's kind of serious. So that's like saying if we're working in meters, we're off by a centimeter. And that's, you know, probably maybe not noticeable, but if a lot of those sorts of errors collect up, then it can give you problems. And I've had that happen to me. All right. So this is a pretty good code section coming together here so far. Let's put these in some brackets. And these two in some brackets. Gonna bring back the previous code. What was it? This. And then C was this. And then, and we can leave that alone. D1, D2. It's a floating point playground, guys. We can do anything we want with floating point numbers. So what are we going to see next? The guys at my work would get on my case if I don't put little f's here. Doesn't really matter, but okay. So the next thing we want to see is, what was it? Special values. Okay. Float A equals 1. Float B equals 0. Float C equals A divided by B. What is the result going to be? I will let you guess that while I eat my apple. Is x over 10 not equal to x times 0.1? I think that's actually true. I don't remember. It says it somewhere in Goldberg. Those are both good guesses. It's not 0 though. In fact, I think they're both wrong. This thing pisses me off. Macs aren't perfect, obviously. I don't remember where in this document it is, so I'm not going to spend time trying to do that right now. Let's build it and see. -0, we'll get to that. -0 is cool. All right. What's the line number I want? 60. Thread until 60. Here we are. 1, 0, C. The winner is positive infinity. There is a special series of bits. In fact, I think we can see them. Oh yeah, this will be cool. Yeah. All right. This is the sequence of bytes that represents 1. This is the sequence of bytes that represents 0. It's all zeros. That's actually intentional. That's by design. The people who designed floating point numbers made it so that if you just put a bunch of zeros, then it comes out to 0, which is cool. Let's see what the sequence of bytes that represents positive infinity is, and there it is. And I show you this just to give you a sense of like how a format that normally stores a number can store something called infinity. And it doesn't. Like, it's just a sequence of numbers that every time the hardware sees that, it takes a different path and it thinks about it as being infinity instead of as being an actual number. So, let's do this. Oh, I probably have this wrong. What is it called? It's called float max. There is a positive infinity and a negative infinity. Yeah. Yeah. Max float. What is it? Max float. So this is the maximum number that can be represented by a floating point number. The largest real number that a single precision floating point number can represent. And wow, it's not here. Oh, here it is. Float max. Oh, I just don't have the header file. I don't have the header file. Okay. Include float.h. Good. So, what is it? What is the largest number? Any guesses? Any guesses what the largest number that can be represented in floating point is? In what order of magnitude? And here's a hint. How many? Okay, it's a good hint. Single precision floating point format. How many bits are in the exponent? Right? Because what we have to do is we have to max out the exponent and then we have to max out the significand. And this isn't quite the whole picture because the exponent is biased. So whatever it is, you subtract 127 to get the real number. But if there are 8 bits, 2 to the 8 is 256. And 256 minus 127 is 256 minus 127. 129. So we're going to be about e to the 129. I'm sorry, 2 to the 129. And what is that? 2 to the 129 is about 6 raised, I'm sorry, 6, this e means times 10 to the 38th power. So a 6 with 38 zeros. And let's see if that's what it, and that is what it ended up being. 3 raised, 3 times 10 to the 38. It's the same e, right? That e right there means times 10 to the positive 38. So that was actually a pretty good guess. So a 3 with 38 zeros is the largest number that a floating point number can give us. But as video game designers, developers, we're never going to get a number that big because when we're doing physics well, I don't want to say never, but like for physics simulations, we're not going to get a number that big because we need at least a few digits of precision to be to the right of the decimal. And if you have a number that has 38 zeros at the end, 1, 2, 3, 4, 5, 6, like, I'm going to draw these commas. So we need maybe 3 digits of precision on the right at least. So we need the decimal to be here. We need this digit right here to be able to be represented. So that gives us 30 million meters, which is 30 kilometers radius that our world can feasibly be. In practice, it's a lot smaller than that because then when we need a little bit more... The fuck is that thing? A face? Kappa? What does kappa mean? We need more because we need some elbow room to do operations. So really we're only using like 10 to the 8 or something like that. So that's why you see games that have a few kilometers worth, like, what is that? What is that? I don't know. GTA San Andreas had a pretty big world, but this is a good question. Largest game worlds. What are the biggest ones? I don't want to know. Okay, World of Warcraft, but that's not continuous. Operation Flashpoint. Yeah, I'm talking about like continuous game worlds where you don't have to do a loading screen. Because when you do a loading screen, you can move the origin somewhere else. And that's cheating. Minecraft. What am I talking about? Okay, Just Cause is a pretty big game world, and there's no loading in it. And then, of course, Minecraft. So, all right. Where were we? Okay, so this is the largest number that a floating point can contain. And let's see. Wait. If C is bigger than the max number, print F bigger. So this might be weird because, smaller. Because max should be the biggest one. But infinity is defined to be larger than any real number. So thread until 69. C is infinity. And max is this huge number. But you can see that infinity is bigger than the maximum. So why did they do it this way? Why did they make an infinity instead of having, like, division by 0 should be an undefined result. It should be like not a number or something. Not a number was a good guess. But it turns out, and I think he talks about this in Goldberg. Where's Goldberg? Goldberg. Infinity. No results found. Wonderful. Whatever. It turns out that some operations are just easier to compute if you allow the division by 0 to be infinity. What happens if I put a -1 here? Now C is negative infinity. So we have a positive infinity, a negative infinity, and let's see, how do we do -0, and I think I know how to do it. Float D is 5, and E is going to be D divided by C. Let's see what that does. -0. Is that guy he's not very interested in math. He's interested in the Illuminati. That's fine. So D is a positive number and C is negative infinity. And technically, like strict mathematics, you can't divide by infinity. It doesn't make any sense. You can take a limit of something that goes to infinity and divide by that. But you can't just straight divide by infinity. But that's fine. -0. So there's a bit pattern in floating point numbers that represents -0 instead of +0. And let's see if we can see what it is. Print. Wait, how did I do that before? Yeah. So there's a single bit. The what is this going to be? The 8th bit from the right, I think, maybe the 7th, that represents... Wait, no, that's the last bit. I don't remember. Doesn't matter. There's a single bit in there somewhere that represents positive and negative. Oh, it's because these guys are reversed. It's because we're... Oh. BQSK, biggest math fan. Okay, so... This is the format for floating point numbers. You can see the sign bit is all the way on the left. But because this Mac is an Intel processor, and Intel processors are little endian, the order of the bytes is reversed. And so the last bit comes in the last byte. The first bit comes in the first bit of the last byte instead of being the first bit. So basically what's going on here is to represent negative infinity, we've flipped the sign bit on, but left, I'm sorry, negative 0. To represent negative 0, we flip the sign bit on, but all of the other bits are 0. So how do we get NaN? Because we want to be able to do stuff with NaN. I don't know, should I kick him? I actually forget how to get NaN. 0 divided by 0, you think that'll do it? Let's see. I think that will actually work. I think you're right, actually. Thread to 82. Oh, wait. What? 0, please. Thread to 82. There it is. Thank you. So, not a number. What does that mean? It means you did some kind of invalid operation, like 0 divided by 0, which is apparently the only thing undefined in floating point number. But the question is, how do you test if you have not a number? In other words, if you've done a floating point, if you've done an invalid operation somewhere in the past. And here's how you do it. If C is equal to C, true. Else false. For every other floating point number, this is guaranteed, for every floating point number other than NaN, you will have C equal to C. I mean, that should, that's just math. 10 is equal to 10, of course. But for NaNs, C is a NaN, and we took the second branch, which means it's not equal to itself. So this is really useful if you've done some crazy physics computations and you want to see, you can do this. Assert C equals C. In other words, make sure C is not a NaN. And I haven't declared assert. I think I just have to assert.h. Yeah. So when I run this code, assert, by the way, means that the program should be in a consistent state. And if it is in a consistent state, like a valid state, then whatever I put in this parentheses will be true. So if it's true, then nothing will happen. If it's false, I get sig abort. And why did it sig abort? Because if I go to the frame that caused the sig abort, then it shows me the exact line where I went wrong. So does that mean that there's no binary value for NaN? There is. Let's see the binary value for NaN. X, C, 4. There it is. So the first 8 bits are on, and then this, what is that? I'm so bad at reading hex. C is 2, 3, 4, 5, 6, 7, 8. Oh yeah, okay. So they've filled out the entire exponent and sign. So all of the exponent and sign bits are on, and then the fraction bits are all at 0. And that means, like, that actually could be a number, but the hardware, like, the people who designed this says that the number that represents, you just can't get it, and it's going to be NaN instead. So it's just like infinity when the hardware sees that pattern of bits, it goes the other direction. It uses a different, like, how do I say this? It uses a different path, like a different code path, sort of, and it doesn't. And the way you detect it is, yeah, you use C. How can C not be equal to C? Because C is not a number. Like, the rules are just off once you get to NaN. It's a value that should never be there, but sometimes is because you made a mistake as a programmer, and you have to be able to detect when that happens. And this is the way that they specified to do it. I mean, I wish it could be more interesting than that, but hope that answers your question. Okay, that was a lot of cool stuff, and I don't think I want to do anything else with the code section of the video. Let me go back to the planning sheet and save that, and go back to my previous file. This. Okay, I talked about all the special values. I talk about the floating point operations. Great, I'm glad you get it. And then we're going to talk about one type of error. Okay, I'm ready. Guys, I'm ready. I'm ready to record this video. This is the boring part of the stream, where I just record the video and I take 5 takes to do it. Where am I here? Yes. Hopefully it won't take me 5 takes. Hopefully, because I've just explained all this is my hope. Because I just explained all this to you guys, I can now do it in like 1 take. Oh, wait. Yeah, pressure's on. No, wait. Wait. I like how all my files are called untitled. I'm not very organized. Yeah, I think I want to just... Because this way I get to keep the header. I'll just erase everything but the header, and that way the header is consistent between all the videos. I mean, I could just write floating point numbers again, but... And I wish I could find a way in Mischief that I could, like, draw a box. Let's see. What is this box? What is this box? Delete. Delete. Oh my god. Edit. Fill. No. Let's just do it the boring way. My eraser is huge, thank goodness. It's the biggest eraser they'd let me have. Okay, and close some of this stuff. No, I don't care. Close some of that. Yeah, that's good. And open Camtasia. For those of you who periodically ask what I use to record my videos, this is it. Turn the camera off. Go to my custom region and audio works and start recording. Think for a moment. Okay, welcome back to Math for Game Developers, and today we're going to continue our discussion of floating point numbers. This time I have the stream joining me. Hello everybody in the stream, and thanks for joining me. I'm having a great time. Let's start. So last time we discussed that if you have a floating point number, it's represented in this format. B1 times 10 to the E1. And if I have another one, it will be, see, A and B are bad letters to use. Already, I'm screwing up this video because I already have a B here. I'm going to use an S here instead. S. This is just take one. We're throwing out this take. In fact, I'm just going to even stop recording and delete it. See, I already flubbed it. Awesome. We're going to get a timer out as well. Timer on my tablet. Timer. Stopwatch. Google stopwatch. All right. So last video we discussed. Sorry, I said I wouldn't bang on the desk, and I did. We discussed floating point numbers and how they are stored in a special format. And so S2 times 10 to the E2. We have these two floating point numbers, and we want to multiply them together. We want A times B. So that is replacing our format times S2 times 10 to the E2. Well, this is just like scientific notation. We covered this in grade school. So I'm not going to spend too much time on it, but it looks like this, times 10 to the E1 plus E2. Because multiplication is commutative, this is super easy to do. And now we have another S, S3, and we have another E, E3, that's equal to E1 plus E2. And so we have a new floating point number, C, which equals S3 times 10 to the E3. But what happens when we add? And I'm going to stop using S's and E's. I'm going to add with real, actual numbers. Let's say we want to add 5. No, I'm not recording. I'm like, this is just a dry take so that I can, yeah. 5 times 10 to the, what numbers was I using before? 8. I think, plus 2 times 10 to the negative 4. Now I don't have like terms, so 8, so I can't add these two together. So what I need to do first is I need to convert, I'm going to convert the second floating point number to be the same term, the same exponent as the first floating point number. So that will be 5 times 10 to the 8. I can leave this one alone. Plus, and now I need to add, what was it? 8 plus 4 is 12. This is coming out a different number than before, but that's fine. 2 times 10 to the 12 times 10 to the negative 12 times 10 to the negative 4. Wait, that's not what oh my God, I'm bad at math. 8. negative 8 times 10 to the negative 4. And then I can take this junk right here and make it part of my significand. And I'll get 5 times 10 to the 8 plus 2, and let's see, what's negative 8 minus 4 is negative 12. So I need 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 10 to the 8. Now I have like terms, and I can add, and I get 5.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 10 to the 8. But remember what we spoke about last video. In a single precision floating point number, we only have about 8 units of precision. And so the hardware is going to have to truncate this at 1, 2, 3, 4, 5, 6, 7, 8 digits. And so the rest of this floating point number will be shifted out. This process that I just did is called shifting, and these digits that are too small get shifted out. And so the result is 5 times 10 to the 8. And this is problematic because we have 5 times 10 to the 8 plus 2 times 10 to the negative 4 is 5 times 10 to the 8. We've completely lost the number that we've added, and it's not even there. So this is an example of round-off error. Round-off error. And it's the first type of error that we're going to encounter in our journey through numerical analysis. And it's important to remember because it means that if you are close to the center of the world and all the numbers that you're adding together are small numbers like 1 and 2, then you can do math just fine, and you can do all your physics simulations, everything will work fine. But once you go way out into the edges, like in Minecraft, if you just walk for days and days and days, and the numbers that represent your position get very big, then at some point your additions start losing all of the precision in the lowest bits, in the lowest digits. And your physics simulations will get bad. And this is why there's a limit on the size to game worlds. So that's one thing to remember. And now we've covered everything in the Blackboard section that I wanted to cover. And we are at 5 minutes, which is good because I want plenty of time for the code section. So then we're going to go to the code section of the video. And we're going to see a bunch of, okay. I don't feel like I need a dry run of the code section. So let's erase this and record the video for real. And hopefully I'll get it right on my first try, guys. Which is really my third try. And everybody leaves the channel. And then we'll talk about, the next video will be root finding. Actual numerical analysis and not just floating point stuff. So starting this again. Welcome back to Math for Game Developers, where we are recording today's video on stream, live, and hopefully I don't screw up and have to do 20 takes. And last time we were talking about how floating point numbers come in formats. So for example, just like this, the floating point number A is going to be represented by a significand part and an exponent part. And B will have a different significand and a different exponent. Now let's say I want to multiply A times B. Well then, just copying from this over here, I'm going to want S1 times 10 to the E1 times S2 times 10 to the E2. Now this is just like scientific notation, and if you covered that in grade school, great. Otherwise, I will put a link to the Khan Academy below, but it's pretty straightforward. You get S1, S2 times 10 to the E1 plus E2. And now I have another number that's back in the floating point format. Here's my new significand. Here's my new exponent. And so if I want to know what C is equal to A times B, then This will be C, and it will be equal to S3 times 10 to the E3, where S3 is just, these things are equal, these things, and these two things are equal. So now I've made a new floating point number. It's this is what the hardware does every time you multiply floating point numbers. So let's do it again, except now let's add A plus B. And I'm going to use some actual values so that we can see what's going on. I'm going to use 5 times 10 to the 8, and I'm going to add it to 2 times 10 to the negative 4. And now I can't just go ahead and do this addition because I don't have like terms. Here I have a 10 to the negative 8, and here I have a 10 to the negative 4. So the first step we need to do is make like terms. And I'll just do that really quick so that we can see what I'm doing. Times 10 to the 8 times 10 to the negative 8 times 10 to the negative 4. And now I have a 10 to the negative 8 in both terms, and I just take these extra exponents and combine them into the significand. So that will give me 5 times 10 to the 8, that hasn't changed, plus 2. Okay, hold on, we need 12 zeros, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2 times 10 to the 8. And now I can actually add these guys, so we get 5.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times 10 to the 8. But we learned in our last video that floating point numbers have a limited amount of precision, and in single precision floating point numbers we can only store 1, 2, 3, 4, 5, 6, 7, 8 digits. And so everything after this 0 right here gets cut off. Now this is a problem because you'll see before that we had 5 times 10 to the negative 8, we added 2 times 10 to the negative 4, but the result is that we still only have 5 times 10 to the negative 8. So it's like we added 0, but we didn't. We added an actual thing that was completely lost by the calculation. And this is an example of round off error, which is the first type of error that that we're going to be encountering in our adventures in numerical analysis. So this is a problem because if you have a very large game world, then if you're near the origin, if you're near like the 0, 0, 0 coordinate, then all the numbers that you use to do your calculations are small, and there are no big numbers, and so that's fine. But then as you go out into the very far distances of the game world, then you start getting some big numbers in there, and you want to add a small number to them to make the player move a little bit to the right, and you don't have enough precision to do that. So this is like a limitation for how big game worlds can physically be without going through loading screens or something like that. So there are a few operations to watch out for when you're using floating point numbers. One is doing a big number plus a small number. One is a number, I'm going to call it A, minus B, where A is about equal to B. And this will suffer the same sort of problem. You'll get inaccurate results. And then someone in the stream pointed out that I'm very appreciative for, if you have A plus B plus C, that is not always exactly equal to A plus B plus C with the parentheses in a different place. So these are some things that you can do that you should try to avoid, and keep in mind when you're using floating point numbers. Most of the time they won't work. They won't be an issue, but every so often they'll come and bite you, and so it's good to be aware of them. Now let's go to the code section and look at some actual floating point numbers at work. Good. Okay, we're done with that. That was not terrible, actually. I'm reasonably happy with that without take. And let's save it. Here. Untitled.camproj. And go to the code section. How am I going to do this? How am I going to do this code section? I'll do it like this. View, layout, single. I think I'll do a full screen recording for the, I think that's how I've been doing it ever since I switched to Sublime. I've been doing just a full screen code section. So I will do that. And that way I can thumb back and forth between the debugger and the so is it built? Good. Let's go back to the recorder, start recording. And this time we have full screen. And we'll come over here. Okay, we're what? Where'd it go? Where'd it go? There it is. All right, let's do the code section real quick. So here we have basically a playground where we can screw with a bunch of floating point numbers and see how they work and what they do. And this is already compiled and ready to go. So I'm going to go to the debugger. And this again is a command line debugger. So don't be too worried. I'm just going to start the program and I'll step us through the process. So first I'm going to assign a big number to a floating point and then a very small number to a floating point. And that's A and B. And let's see the contents of A and B now. One is 1000 and one is 0.00009999, which is weird because we tried to assign 0.0001, but what we got is something slightly different. And this is because computers store floating point numbers in base 2, and not all numbers in base 10 are exactly representable in base 2 with the amount of precision that floating point numbers have. So that's something to be aware of. Most of the time it's not going to be a big issue, but sometimes it is. So let's see the result here when we add A and B, and we have C is now 1000.00012. And that's weird because A was supposed to be less than the value we put into it, was 0001. But when we add the two together, we get something bigger than 1000 plus 0001. It's slightly bigger by, a very small amount. So floating point operations can be a little bit wonky in the last digits. And that's something to watch out for. Again, usually it's not a big deal, but then when you need to know about it, it's good to be aware of this stuff. So we're going to add one more 0 right here just to see what happens. Just to make the difference between the big number and the small number a little bit bigger. And you can see that now the 0.00001 has been shifted out of our result entirely and just lost completely, and we have A plus B equals A. So there you go, something to look out for. Let's continue on. I'm going to assign A, B, and C in this way. I don't know why I put B before A, but I did it that way. And then I'm going to add them together in two different orders. And I'm going to exploit what we just talked about, how a big number and a small number can lose the small number in the addition. I'm going to exploit that to get two different results in D1 and D2. And let's see what they are. Here's D1, 0.00109 and some junk, and here's D2, 0.00107 and some junk. So not only is it inaccurate, but it's inaccurate in only the third digit, which is a pretty significant difference. So this, again, is only happening this way because I found specific examples that that exploit this difference. Usually it's not a problem. So, but again, this is how floating point numbers work. Something to be aware of. So continuing down in my program, I'm going to assign A the value -1 and B the value 0, and then I'm going to divide A divided by Z. Now, what result am I going to get? As you know from math class, A divided by B is undefined. It does not have an answer. But when we're dealing with floating point numbers, it does have an answer. Your computer will assign the value infinity, because I had -1, it assigns negative infinity to this number. Now, how can that be that we have a floating point number, which is just a bunch of digits in the computer, and it represents something other than a number? That's because when they decided how floating point numbers would work, they decided that certain bit patterns would represent special values. And this is the first of those special values, infinity. And infinity has a weird property that it is bigger than any other number. If you take the maximum number that can be represented by a floating point, and I'm going to store that in this variable max. Actually, let's see how large it is. It is about 3 times 10 to the positive 38. It's a huge number, but I'm going to test to see if c, which currently has, it currently has negative infinity. Let's make it positive infinity and run this again. Now it's positive infinity, and positive infinity is larger than the largest value that floating point numbers can store. So as you can see, it took the first branch, which prints bigger. There's bigger right there. So that's interesting. Now, remembering that c is and now I have to turn this back to negative. Should have planned this better, I think. So let's put that back to negative. So I'm going to put the value 5 in D, and then C is back to being negative infinity. And what happens when we take 5 and divide it by negative infinity? That should make no sense if you think about it in a purely math term, like purely in math terms, but the people who made floating points decided that it should be equal to print E -0. Wait, what's -0? What does that mean? That makes absolutely no sense. 0 isn't positive or negative. Everybody knows this. But floating point numbers actually have 2 different representations for positive and -0. Positive and -0 will always give you the same result if they're used in a computation. It's just kind of an oddity that sometimes for very specific algorithms can matter. But in this case, most of the time, again, I feel like I've said this 4 times by now, most of the time it won't really matter terribly much. But this time, in a very rare occasions, it can matter. Okay, fine. So now what happens if we say A and B are 0 and we do A divided by 0? What do you get then? Well, we learned that another number other than 0 divided by 0 gives infinity. But 0 divided by 0 is actually called an indeterminate form. It's a little bit different. And it gives you another special value, print C, called NaN, which stands for not a number. This, again, is just another series of, another pattern of bits that the people who made the floating point spec decided would be a special number. And usually, if you see NaN in your code, if it turns up in your floating points, it means you've done something wrong. Like, dividing by 0 can kind of sort of happen sometimes in a lot of algorithms, but 0 by 0, that should probably never happen. And if you do that, it makes absolutely no sense, and you should get just an erroneous result. And that's what NaN is. Now, how do you detect if you have an NaN? Well, NaN is the only bit value that if you compare it to itself, it will tell you that it's not equal to itself. So I said if C equals C, and C has NaN in it, and that should be true all of the time, and it will be true for any other number except NaNs. And so this is a way that you can use to detect if NaNs are in your code, or NaNs as they're called sometimes. You can use assert C equals C. C is equivalent to C. And because C is NaN, this assert will fail. Bam. It gave me here's the stack trace, and it basically, the program's about to die now because the program is in an inconsistent state where I did something wrong. I divided 0 by 0. And that's not allowed. So that's the special of values and operations in floating point numbers. Next week, we're going to get into, or right now, if you're watching the stream, we are going to get into root finding, which is the first actual numerical analysis stuff that we're going to do. I'll see you then. Stop recording. Great. Great. It's so beautiful. How'd I do, guys? Go in the fucking... No. There we go. Total length. Oh, 15 minutes. Oh, I'm killing myself here. What's wrong with me? See, you shoot for 10 minutes and it never happens. It never happens. Okay, I'm going to do the actual editing offline because editing is boring. Even more boring than math. No, math is incredibly interesting. Everybody loves it, of course. But yeah, I'm going to do it offline so that we can get onto the root finding, which we will do after a short break for me that I will take right now. I'll see you guys in a little bit. Thank you again for joining me. I'll be right back. It's fine, bud. I'm just going here. Okay, bud. Just getting a snack. Okay. Let me take the dog out real quick before we get into this. 5 minutes, I swear. I'm back. And we're going to do bisection method now. First, we have to discuss what is root finding, and let's find an image from the textbook. Hey, welcome Aussies. Sorry I got started so early in the morning. Yeah, actually we're just getting started on root finding, so you jumped in at a good time. I did one video and I'm starting the next one. But none of the stuff in the previous video is required to know for this video. So you should be fine. And bisection method. This is what we want. Bisection method. Let's see, what's that? Okay, here we go. So, what is root finding? I don't really like this picture. I'm going to draw my own. Root finding. What is a root? Why do we want to find it? Roots. Okay. Let's say that, not even. Let's say that this is the terrain in your game. And there is a projectile that has been, put a little tank here. Tank, it's a tank game. And then here's another tank. And they want to kill each other. And this tank fires a projectile. Okay. And you want to find at what point the projectile is going to strike the ground. Well, if we say that, if we simplify this a little bit, and we say that the path the projectile follows, it can be described by a function, and each point in the terrain can also be specified by a function, then the root is the point at which these two things intersect. In other words, let's see. Well, that's not really the root. That's the solution to the series. The root is if I take f of x minus g of x, and I say, when does that equal? No, sorry. I pronounce route, R-O-U-T-E, route, not root. Yeah, it's so pathfinding. But I did some pathfinding videos like A star and Dijkstra's algorithm and stuff. So, what else could be considered route finding? Well, not this anyway. So the root finding, root is another word for zero. When is the difference between those two functions zero? That is the root. So I have one root here, pretending that the projectile would fall, infinitely, and yep, totally. And then I have another root here, right where the tank is, pretending that if it had gone back in time infinitely, it would go through the ground. So I really have two roots to this equation. So this equation will be 0 when f equals g, and you can see that f equals g at 2 points right here. Now this one we don't care about. This is the one we want to find. So I'm going to say f minus g is equal to a new equation that I call h. and I'm going to graph H. All right. And this is, let's see, how should I do this? I'll just, yeah, right here and right here. So you can see that before this point, F is less than G, and so F is negative. And then at this point it hits G, and then it does some crazy stuff, and then it hits G again, and then it goes less. So this right here is H. This right here is H. Hopefully that makes sense. You can see that H is like the altitude of the projectile. And what we want to know is when the altitude gets to be below 0. So we want to do root finding on that point right there. And there are a lot of different methods to do root finding. And okay, well, why do we even want to do root finding? Maybe we want to show like a little target on the ground of where the projectile is going to land. That's a pretty straightforward example, but like I've been to talks where people use root finding to determine if you have two physics objects like this, and one's moving like that and the other's moving like this, then at what time are they going to intersect? You want to know when they're going to intersect because you want to know when the collision is going to happen so that you can make them split apart. So there are really a lot of different cases when you can use root finding. I think I'm going to pull up go to my channel and pull up a video that I posted a few months ago. I'll have to skip past all the videos of my dog. This one. And in this video, which I don't think I ever posted publicly, but you can see could be used for AI to predict, there you go, projectile landing, or could be the reverse used to calculate projectile angle. Yes, it could, right. So you can use this for a lot of stuff. Like so for projectiles, it's a really simple function. It's just a parabola. And it's pretty, like, you don't need root finding to solve that, to be quite honest with you. But if there are a lot of other factors, if the function is a little more complicated, and you can't just do an implicit solution, then you can use root finding to figure out what angle you need to point at, just like you say, Simon, to get the projectile where you want it to be. So that perfect angle. So yeah, your function is a function of the angle at which you fire it, and when it hits whatever you want it to hit, that you consider the root of your function, and you do root finding to figure out what angle gets you to that point. And that's a great example. Here, in this, like, this is just a little OpenGL demo program that I wrote while I was still in school, and the caustics on the ground, like the light waves that you see on the ground, that are simulating light falling down through the surface of the ocean and striking the floor. Those I programmed using root finding techniques. So you can even use it in graphics. Like, you can use it in a bunch of different places, and I'm not going to play that whole video now because it's boring. But okay, so now we know what root finding is. There are a bunch of methods, and we're going to talk about, first we're going to talk about bisection method. Bisection. Thank you. So, story time. I just got out of school, and I went back to school a little later in life. I was a mathematics major, obviously. It is on YouTube, I guess. Here's the address. You can watch it. Yeah, a procedural effect in the vertex shader. It wasn't a vertex shader, it was a fragment shader. But Right, so this, I took a computer graphics class because I needed an easy class that quarter, and I already know computer graphics. Because I was taking a bunch of other honors classes and stuff. And this was an assignment that they gave me to make a video like this, and it had, you know, how assignments are in school. It has to have, you know, such and such. It has to do this, and you have to do that in it, and so I went and I wrote this, and I turned it in, and I think it was a little bit unfair because the person who had, like, the class voted on the best video, and the person who made the best video got extra credit points, and I kind of feel bad because I have all this extra experience from before I went back to school that you know, let me make a cool video, and so I got the extra credit points, and I'm sure everybody else was like mad at me. So anyway. All right, so you have some function. At this point, we don't even care what it is anymore. We've just decided that we like root finding and we want to learn some root finding methods. And we know that it must pass 0 at some point. Okay, so you have to know this for sure before you can start this method. You have to know for sure that it must pass 0 at some point, and it has to pass 0 between this point and this point. Okay, so this is h. This is our function h. And so we know that h at some point x1 is greater than 0. Here's x1. You can see that h is greater than 0. And then at h point x2, h is less than 0. So here's x2, and you can see that h is less than 0. So we want to find the point at which h is exactly equal to 0. Now, if you're a programmer, you're thinking about this, and you're thinking, well, I know a technique that lets me find data in a sorted list. So that's kind of like root finding. Funny if you did a video with diagrams of you in your school life. A video of diagrams, listen, I just want to forget about school, honestly. So you mean like a video of how I did in school? I failed half of my classes, so you probably don't want to learn how to do school by me. I mean, I could have done better, but I'm going to try, I'm going to try and get, I'm sorry, I missed it last time you said that. I'm sorry about that. I'm going to try and get this on YouTube, absolutely, so that you can see. I have to deal with some, I don't know how to make Twitch do that, but I'm going to try and figure it out and make it do it. I screwed up and I didn't check a checkbox last time we did the stream, and so I forgot to, so I wasn't able to get the last stream up there, but I think I should be able to get this stream up there. So anyway, okay, root finding, bisection. So we learned how to do binary searches. You have a list that's sorted. How do you learn math? You sit down and you do it. There's no trick. You just do a lot of math. I mean, it helps to like math. And I think a big turning point for me is when I realized that I do like math. It can be used for a lot of things. And just because something is hard doesn't mean that you should dislike it. And math is hard, so a lot of people dislike it for that reason, I think. But once you realize all the things you can do with it, then there's a reason that you're doing that hard thing. It becomes a lot easier to push through the difficulty. But there's no shortcut. If you're Alexander Grothendieck, then it all comes easy to you, but most people aren't that. Yes, I got that request, and I put the hierarchical bounding volume trees. I did put in my document of things to do. It's not going to be for a while because we have a lot of numerical analysis to get through, and I don't like to skip around very much, but it's in my list. I'm going to do that and a few other scene management techniques, I think, in the same series. It might even be the next series that I do. Okay, so we have a list of numbers, and they're sorted, they're in order, and I want to find the 8. And so I'm pretty sure I did in a previous video a binary search where you split it in half and you say, okay, well 4 is right. Well, you look, maybe do it this way. You look at the middle element, you say 4 is less than 8. So then you look, so the 8 must be to the right of the 4. And then you split that in half. And you see, here's the halfway point, 9. Well, 8 is less than 9, so it must be to the left of the 9. So you have a new range, you split that in half, and eventually you drill down to where the 8 is. And that's what we're doing here. It's the same thing. If you have this range from A to B, and you have this function that goes like this maybe. Let's have only one root. Okay. Then you cut it in half, and you test h of, so let's see. This is x1, this is x2. What's the halfway point between x1 and x2? It's the average of x1 and x2, x1 plus x2 divided by 2. And so we're going to put that here, x1 plus x2 divided by 2. Actually, you know what? Let's just call that x3. So h of x3, we're going to evaluate h at x3. Is it going to be bigger than 0 or less than 0? Is it going to be positive or negative? We know that x1 is bigger than 0 and x2 is smaller than 0. So x3, h of x3 being bigger or smaller than 0 is going to tell us information. Here we can see that it's less than 0. So that means that the intersection point has to be to the left of the this average point. Cool? And then we do that iteratively until we find the root. Well, but what does that mean, find the root? Because, so someone mentioned before, could you use this to find the value of pi? And what you're looking for is sine of what equals 0 between, x is between 3 and 4. And if I keep doing averaging like this, then I'll test at 3.5, and then I'll test at 3.25, and then I'll test at 3.125, and let's see, 3.14. What was the joke? And so on, and oh, pi was a joke. Yeah, well, but you can use this way to get pi. 3.14159 is what we want, and you see we're getting closer to it, but we're never going to get it exactly because pi is irrational, and all of these numbers that I've been writing are rational. So we have to have some way to decide when we've done enough. Like, at what point have we gotten close enough to pi that we're good? Sine x equals 0. This is root finding that I'm doing right here. Let's see, how does this look? Here's pi. Here's sine. And this right here is pi. And this is what we want to find. And we're basically doing this root finding. And we're going to drill down. We're going to get closer and closer to pi until the point where we have xn. And here's pi. And here's xn plus 1. And the difference between xn and pi is going to be less than some number epsilon. So ahead of time, we're going to decide, okay, epsilon is my acceptable error. How close do I want to get to pi? Or whatever other number we're trying to find. And then we iterate on this algorithm until we get within epsilon of the number that we want. And then we call it a day. We say, we're done, and this bisection technique is over. So, let's see. Let's organize our thoughts here. What do we need to know before we can do bisection? One, that there is a root. If there's no root, obviously bisection's not going to work because, the function will be positive everywhere. Two, we need to have a bracket for the root. In other words, we need to find a place where to the right of the root and to the left of the root, where between those 2 points, to the left and to the right, where between those 2 points there is a root. So we need to find a bracket. We need to know that this fits well with both the precision issues, yes, and say using this algorithm with delta time, since you always need a threshold. I'm not sure what you mean by that, using this algorithm with delta time, since you always need a threshold. Yes. But yes to the first half, it does fit in. So the bracket should contain exactly 1 root. Because let's see what happens if it contains 2. Something like this. It'll contain 3. How about that? And this is our bracket right here. So you can see at the beginning of the bracket, h is negative, and at the end of the bracket, h is positive. But inside the bracket, there are 3 roots, and if we do this root finding, then we don't really know which one of the 3 roots we're going to find. So, so it's definitely preferable if we have only 1 root inside of the bracket. Okay, so we know all of that stuff, and we need to decide on an error level. Honestly, my approach to error is sometimes I do it the hacky way, and instead of deciding on an error ahead of time, I come up with a number of times that I have to iterate in order to be sure that I'm below the error. Like, I know that if I iterate this 5 times, then I'll definitely be inside the error no matter what. And so I don't bother like doing this check to see if it's less than the error. But then you have to, be really sure that you are going to be less than whatever error you need to get at. So there are a few different ways of doing that. But then the benefit is that this check, if you watched my optimization series, then you'll remember that this conditional is not very well predictable by the processor. And so that can slow things down, sometimes even more than just adding, 1 or 2 more iterations. So, and then let's see, what are the steps? Steps to the algorithm are start with x1 and x2. X1 and x2 are real numbers or floating point numbers. Oh, let's say we're measuring the distance between 2 objects. We can't do just if distance equals 0 because distance involves positions which are multiplied by velocity. Yeah, as your character, right. It'll never be perfectly 0, right? So we have to find some kind of epsilon that we're willing to test between. I see what you mean now, and you're right. So step 1 is we have our x1 and x2 that we bracket, and then we let I'm going to say xn equal xn minus 1 plus xn minus 2 over 2. So we're going to start with n equals 3. N is bigger than or equal to 3. And then we're just going to keep going up. And then if h of xn is greater than 0, then you iterate on the... Wait. Okay, I have a problem here, and we're going to see how my textbook does it. Textbook. Yeah, I need to do this a different way. Textbook is right. Okay, we're going to do it this way. We have A1 and B1. So the problem that I ran into is that I'm not really keeping track of what my x's are very well. And I need to distinguish the left side of the bracket from the right side of the bracket. If I just have a bunch of x's, then I don't know where the bracket is. So I need to always make sure so I'm finding a new, when I draw a new line here, that's either going to be the left or right side of the bracket, and I have to figure out which it is, and then I have to keep them separate. So I'm going to use a's and b's instead of x's. That will work out better for me. So x, I'm going to keep x here, and this is the sort of stuff I have to figure out before I start recording the video, right? So here's a n minus 1 and b n minus 1, and now n will be bigger than or equal to 2. Yeah, n will start at 2, and if h of x of n is bigger than 0. So let's see, we have our root here. Here's the left of the bracket, here's the right of the bracket. If it's bigger than 0, that means the intersection has to be on the left. So we're going to say a2 is equal to, I'm going to do an assignment here. a2 gets the value of a1. Let's use n's. an gets the value of an minus 1. Definitely. And bn gets the value of xn. Whereas if h of xn is less than 0, then we have the other picture like this. And here's my bracket. My test is wrong. My test is wrong. So what doesn't matter is that it's bigger or less than 0. What matters is that the product of the center point and the edge point is negative. I'll show you what I mean. So here we have h a1, and here we have h b1, and here's h x1. So if we take h x1 times h b1, then this is positive and this is positive, so this is bigger than 0. So our bracket is not between x1 and b1 because the product of those two is 0, so it means it never crossed the axis, the x-axis. If we do h of a1 times h of x1, so that's this guy times this guy. Now a positive times a negative is less than 0, so we know we must have crossed the axis, and I think that's what the textbook says. Yeah. If it's greater than 0, yeah, that's how it did it. Good. Hope everybody followed that logic. So if h x1 times h a1 is bigger than 0, is less than 0, then the intersection happened on the left side, and then this stuff is good. Otherwise, it happened on the left side, and we need to make the new left bracket be the midpoint, and the new right bracket can just be the same as the old right bracket. Okay, and then the very last step is if, so now we have to decide how are we going to figure out if we've actually found the root. Because we don't know what the exact value is, like we did here when we said xn minus pi. That is a little bit disingenuous since it assumes we already know what pi is. And if we already know what pi is, then why are we trying to find pi? But I think probably the best approach to do here is if bn minus an is less than epsilon. If bn minus an is less than epsilon, then we have to be, so I'll write this out over here. Bn minus an is less than epsilon definitely implies that bn minus, I never actually came up with a name for the root. What does the book use? What does the book use? P. We'll use P. Is less than epsilon. So here's the picture for that. Okay. Here's an, here's bn, and here's p. Here's p. So that's saying if this distance is less than p, then this distance also has to be less than p. I mean, just looking at the picture, that obviously has to be true because the distance to the root is strictly less than the distance to a. So if this is, let's reverse this. If it's bigger than epsilon, then go back here. And that's it. That's bisection method. Let's check the textbook and see if I screwed anything up. Set I to 1. FA is the function value at A. Oh, so they have a cap on the number of steps that it can take as well. I don't really, I mean, maximum number of iterations. I don't really feel like that's necessary for this algorithm because it's guaranteed to terminate eventually in a logarithmic number of steps. So I don't care about that. I don't know why they put that there. So you find the average. This is the same formula I have. It looks slightly different. And then you find that midsection P, and then you, okay, good. I equals I plus 1. I forgot that part. That's important. But the rest is the same. I mean, it will, your epsilon is going to be, okay, so here's the thing. 1 over 2 to the n is going to be, assuming that like if an equals 0, just for simplicity, I'm sorry, if a1 is 0 and b1 is 1, then at step n, bn minus an size is 1 over 2 to the n. Do you see why? Because every time you cut it in half, and so, you know, whatever. And so, so at first that width is going to be 1, and then it's going to be 1/2, and it's going to be 1/4, and it's going to be, you know, and every iteration it's going to get cut in half, and so 1 over 2 to the n is always going to be the width. And so if your epsilon, it doesn't matter what your epsilon is, there always exists an n such that this is going to be less than epsilon. And if you want to find out what n that will be, we'll solve this equation. 2 to the n minus 1. Let's just use n. Doesn't matter. And so, yeah, log base 2 of 1 over epsilon is less than n. So when n gets bigger than log base 2 of 1 over epsilon, you will have an answer. Guaranteed. Like, let's actually run that through a calculator so we can see. Open the calculator again. So let's say let's get a really small epsilon just to illustrate the point. What is a tiny, tiny, tiny epsilon? Tiny, tiny, tiny epsilon. That will be our epsilon, okay? And now we have to do 1 over that. So raise it to the -1, and we get a big number. And then we say log base 2. There's no log base 2 here, so I'm going to use the trick where I do a natural log, and then I divide it by 2 natural log. 36. After 36 iterations, even with that tiny, tiny, tiny epsilon that we decided on, that I decided on, it still finds an answer, guaranteed every time. So I don't really think it has much value to write. I mean, really, like, so this is why I was saying before that with bisection, you can calculate how many iterations you're going to need ahead of time. You don't really need step 4, right? We just calculated how many iterations we would need. Step 4, unnecessary. So I just like 36. Usually it's not going to be the smallest 36. It's going to be a number like 5 or 6. Well, they're mathematicians, not computer programmers. I mean, they're probably computer programmers too if they're numerical analysts. So for most of the algorithms that we're going to use, that we're going to look at, it is a good idea to have that number of iterations because something could possibly go wrong and then you'd have an error condition. They're probably just throwing it in there for completeness. But since we are a discerning group of experts here, we're going to just omit that. Because everything that I write, I have to explain, and I don't want to explain it. Because it's not necessary, so I don't have to explain it. So I'm not going to. Now the question is, well, before we go on, because that was really cool, and we all like numerical analysis, we'll take a sneak peek at some of the methods that we're going to learn next time. This one's called fixed point iteration. A fixed point is a point in an algorithm in a function where the function is equal to its value. In other words, y is equal to x. And if you satisfy a certain series of conditions that I'll explain next time, then you can find a fixed point by running the result of an algorithm like the output of a function through itself. So you have g of x, and that equals x2, and then you do g of x2, and that gets you x3, and then g of x3 is x4, and so on. You have to make sure that you're satisfying some special conditions, but if you keep doing that, you will eventually get you an x value where g of that x value equals itself. That is fixed point iteration, and the last one is the coolest one, which is Newton-Raphson. Newton's method, oh man, actually, no, I did cover derivatives in a previous video. Not everybody watching this stream might know what a derivative is, but let's see if we can find a good picture that will explain it. Oh, here we go. That's the picture. So for each point, you use the first order. So, okay, for each point. Well, Newton's method converges very fast, and it's an amazing method. It has some drawbacks, which I'll talk about when we do it. But the basic idea is you use the slope at a point as an estimate for the root. So if this is, where we start, then we find the slope. Okay, no, we start down here. We find the slope at that point, and it's a pretty bad estimate of the actual root. But then we iterate this. We use the slope again, and we find another estimate, and then you draw another slope, and if you keep doing that, you eventually get a really good estimate, and this converges a lot faster than bisection method does, but it has some drawbacks. So those are the sneak peeks. Those are the sneak peeks of the next few methods that we'll do. But for now, let's see. That was all pretty straightforward, so let's maybe try to... record this video. I'm going to export this so that I can hopefully bring it up on the other screen. Is this going to work? Why is this empty? Oh, I saved it in the wrong damn place. We wanted to save that in Bisection. Save. And export this in Bisection. All right. Bisection. Now actually has stuff in it. Here we go. I'm going to put that on my other monitor so that I can see it. Well, that's good enough. Clear. Yeah, we were joking about that before. The file names don't matter because I organized the directory names. So, once you look inside a directory, it's obvious what stuff is by looking at the extension. So I don't even bother with the, yeah. Thank you, B617, for joining me. See you next time. All right, root. Should actually write neatly because this is going to be recorded. Root finding. All right, so that was actually a lot of stuff that we talked about. And it took like half an hour to cover all that stuff. And actually, crap, the code section of the video, I have no idea what I'm going to do for that. Should there even, I can't do numerical analysis stuff without loading up the code section and showing an implementation. But the problem is that if we delete all this floating point stuff, recompile, and now when we try to actually run the thing, why did I do that? Run, it crashes. Yeah. I like to, I record the code section and the Blackboard section separately. But I found that if I actually do the code section before I record the Blackboard section, it helps. It gives me some context of and some focus of what I should talk about in the Blackboard section. And sometimes I get the math wrong. And yeah, but so the projectile problem is a good problem, but for one, I have to deal with this crash. Like, I like to have it visual, something that you can actually see in an actual game. And for one, there's a crash, so I would have to fix that, and that would be really boring to do on the stream. For two, I would have to, like, you remember what it looks like. The actual, like, in-game thing, the ground is flat. So you would be bisection methoding a parabola with a flat surface, like, why when you can solve that perfectly by just let's take a look at the caustics. Do I have that code lying around? I probably don't. Documents. No, but it is on my GitHub. I know that for sure. Character terrain alignment. I'm not sure what you mean by character terrain alignment. Since when does ground flow? Oh, smooth ground. Like you mean, not looking like polygons? Just to render them? No, and most. Oh, yeah. Yeah, I don't think this is really... Well... Actually, it might be. If you look deep inside the physics engine, yeah. Right. So, back to the drawing. I think you're right. And you have, like, some kind of weird ground, and then you have a character, which is usually just a box. And let's actually draw him touching the ground. Let's draw him a different color. Something like this. That's a box. That's totally a box. And the character moves forward, and you have to find the point. Let's not draw him touching the ground. The character moves in this direction, and you have to find the point at which it touches the ground. Inside the game engine, route finding would probably be used for that. But then, if we can't load that up in our little... our little test game that we made. Words, man, I'm so bad with words. Because the ground is flat, and we could load in a polysoup, but I don't know. That's a lot of work, and I don't want to do all that work just to load in a mesh into that little test program that we have. So, well, let's take a look at the source code. So this is the caustic test. This is the caustic root finding that I do. And let's see. So I guess I'll have to explain this now. So here's the model that I used. I have this sine wave. I'm going to draw it in blue because it represents the surface of the ocean. And then down here you have the floor of the ocean. And then a light ray comes in, strikes the water, and refracts, something like this. And then strikes the floor right here. So, yeah, totally. So if you have a, if you know where your light ray is, and you're looking for where it strikes, then that's fine. You can do that forward. You can just simulate your light ray, do your, index of refraction physics shit, and then hit the ground. Oh, I shouldn't use bad words in the stream. There might be kids around. I keep forgetting. I'm really bad at that. I don't think there are any kids around. Okay. No bad words. So you simulate your ray and you find where it strikes. But when you're rendering, you're doing the opposite. You're looking and you're saying, so for some point on the ground, how many light rays hit it? How bright should I render it? Because at the points where you have a concave surface of the water, I guess that's convex, then you're going to be getting a lot, like the light rays are going to be focused down in a single point. But where it's concave right here, then it's going to be refracting things away. And so you're going to get a bright area here, and then a dark area, and then a dark area, and a bright area, and a dark area, and a bright area. So that's why we need to use root finding, because we need to so let's clear up some of this junk. We say, okay, for this, I'm going to have an estimate, which is that this is the ray this ray right here is the one that I'm going to estimate strikes this point. That's obviously wrong because this ray bounces off in another direction. But I'm just going to use it as a beginning estimate and then do root finding to see where the real ray is that strikes that point. And I do some root finding, and I discover that it's this ray. So that's like a function, right? The function is what is the input ray, and then it has an output. So it's like a ray function, and then I give it a position, and then it gives me a horizontal position. I'll use X then. A position, and then it gives me another position. And I do root finding to figure out where that ray is that's hitting me on the floor. And then another little bit of math. Yeah, it could be the hook. Where was it? Let me actually look again and see. So this is the code that I used. First I do a few bisections, and then I follow it up with a few newtons. And then this weight is given. Yeah, if we're concave down, then the rays are more focused. So yeah, so it applies some kind of weight that's once it finds where the ray came from, then if it says if it came from the lower half of the sine curve, then the rays must be spread out, and if it came from the upper half, then the rays must be condensed together. And it's a really bad model, honestly, and I wouldn't recommend that anybody do caustics like this. I just wanted to do some root finding because it was fun. And nobody else in my computer graphics class would be able to do it. Poor bastards. So, because they're all CS people, they don't know any math, right? They're like, math, ugh, I'm a programmer, I don't need math. Could you code this recursively? Yeah, no, it's just, you mean with a loop. In a loop, and nope, this, like I said before, I just did enough that I knew I would get the accuracy I want, because this isn't a GL, this happens on the video card, this happens in the GPU, and GPUs hate conditionals. They do really poorly with conditionals, and so I just avoided the conditionals entirely by just copy paste here. Here's the bisection. So that is nice, except that this code worked on Windows, and I've never actually compiled it for Mac. And I'm on a Mac right now. And because computers are awesome, I don't think it would be very easy for me to get this code running on. Yeah, see, it's like a Visual Studio solution. You know what I could do though? I could show the video. I have the video on my, it's right here. Because this is pretty cool, I think. It would be pretty good motivation. The video's right here, and I could say, load video load. Video's not loading. I could say, yeah, and that's all this requires. It's just all the other stuff I would have to do. I could say, this is the end result. And let's go code it up, and then we'll go to, like, you know, Sublime, and basically write this exact code right here. And then be like the chef on the cooking TV show that combines all the ingredients in the dish and then says, now here's an already baked one that I cooked an hour ago. And go to the video and be like, here's how it looks. Pretty, huh? Kind of disingenuous for me to do it that way when all of the other ones I've done the other way, but like I really try hard. I try very hard not to do any work for this code, like not to do a lot of work if I can avoid it. That's not always true. I did a lot of work for the graph theory videos. But only because there was really no other way to get the thing that I wanted. But it would give us the, if we did that, it would give us the ability to actually write code and then see what the result is, which is the loop that I'm after. Even if we're not directly seeing the result. I think I can live with that. What do you guys think? Is that kind of BS? Like, hey, you didn't really do it. You just typed in a bunch of stuff and then switched to YouTube video. That's not coding. I think it's okay, though. No, yeah. There are a bunch of those, and yeah, I'm doing something else. I think it's boring to watch somebody write a whole game engine. When this right here is the, oh, but this is no good. This is no good because I had to do this differently. I had to do this differently because... What am I doing here? You know, midpoint. Yeah, I don't know if I should use this exact code. Okay. So the story is, in order for this code to work, I had to code it up like GPU style. And you can kind of see that. It calculates the midpoint last. Like what? Why? Huh? And I had to reorganize a bunch of stuff just so that it would run fine on the GPU. And I used mix and I used sine, and here's me sampling the function, and I sample the function first. I guess that's in order, but this is not really understandable to somebody who I just explained the, oh well, you saw it. You know, those 4 steps that we do. If I explain those 4 steps and then I code something completely different, that would be no good. So here's what I'm going to do. Bisection. I'm just going to code a bisection algorithm, and then I'll show the video. I covered, oh, did I cover explicitly those hacks that I did? The mix and sign? No, because they're not very mathy. Sign just gives you 1 if the value you pass in is positive and -1 if the value you pass in is negative. It literally just isolates the sign. Mix does a linear interpolation. Sign. I should make sure I have that right before I tell you that. Yeah, returns -1 if it's less than 0. Oh, 0 if it's 0, fine. And then 1 if it's greater than 0. And then mix does a linear, and yeah, who cares? Does a linear interpolation. Yeah, it does. And my linear interpolation video is awful, and I want to redo it, but so it should be called LERP or something. Why does this combine together to do that? So, I mean, the whole point is that I use sign instead of saying, you know, if x is less than 0, because I don't want to write that if statement. GPUs hate if statements, and so I use sign to avoid it, and then I reorganize the code to avoid it, and I don't know. It's not very mathy. Like, there are probably other videos out there that cover how to avoid if statements, and I don't know. I don't think it's as interesting as the math. So, well, it is interesting, but this is a math series. So what I'm going to do is I'm going to say float bisection, pass in a function pointer. Okay, wait, float A1, float B1, and then do like this, float, and then write a type def. What is it called? Single variable function or evaluate? Evaluate. Evaluate. F. So save that somewhere. Where should I save it? So the idea here is to write a bisection algorithm. Why am I putting it in another file? So I'll just write the bisection algorithm here. And then do the same thing I was doing with the floats, just okay, so I'll write a simple bisection algorithm, and then I'll show this code, and then I'll play the video, and it'll be almost like the real thing. Yeah, I mean, root finding, there are tons of different ways that you can use it, ton of different things that you can do with it, and obviously I have to leave it, most of it, to people's imagination. So then the question is just finding an interesting function that I can plug into this bisection code so that I can actually write something. So let's see. Yeah, exactly. It's up to you. With great power comes Spider-Man. Let's actually write it. So float x is, oh wait, here's what we have to do. AN equals A1. BN equals B1. So then we say float x equals developing an eye to associate these. But it was right. Yeah. Yeah, one of the reasons I like math is that once you learn a mathematical tool, you suddenly find yourself solving problems that you didn't even know were problems. Like, yeah. You learn a new mathematical tool and you're like, wow, I can do this amazing thing now that I didn't even realize was a thing that I could do before. And now it's like obvious how to solve it. AN equals F of A1 and float, let's do this, HA and HB equals F B1. B1. And so float hx is fx. Good. And then what next? What next? If hx times ha is less than 0, then an stays the same, bn becomes x, and then h of b, this is our h of a, and this is our h of b. So we have to update h of b to be h of x. Otherwise, an gets x and h of a gets h of x. And now we do our test. If absolute value bn minus an is less than, oh, that's right, we need an epsilon here. Float epsilon is less than epsilon, return bn. If we get here, we're in trouble. Something probably went wrong and we should assert false. Because if you need more than 10,000, we talked about this before. Oh, hold on. Still figuring out how to learn it properly. I have 3D math primer for games, so this question's like, oh yeah, dot product with cosine law. Wait, what's cosine law? Cosine law. Law of cosines, yeah. Minus 2. Oh yeah. All right. Right. Do you want a hint on that one? Yeah. This is actually just like, I'll give you a hint. I'll give you a quick hint. Vector, theta. Dot product? You don't prove it, you just derive it. You just derive it. So these two vectors make a triangle. And if we say this triangle ABC, sides A, B, and C, then you can now apply cosine law, law of cosines, to figure out, given the angle and the lengths of vectors A and B, what is the length of side C? But what we're looking at is A dot B equals length of A, length of B, cosine of theta. And you just do a little manipulation. That's the hint. Okay. Good. So I think we coded it up, and hopefully it's correct. And now we have to come up with a function that we want to evaluate. And it has to match this function. And actually, let's just use sine. So I think what I can get away with doing is using from the very beginning of the video this example, and then using sine is okay, since I talked about sine in the first place. And then we're just gonna find, let's find the value of pi. Why not? We talked about that before. We'll find the value of pi, but then with the wouldn't you check for? Yeah, you could. I mean, you could check for equals 0. So with floating point numbers, the probability of it being exactly equal to 0 is so low. It's very low because obviously there are a lot of numbers out there, and the odds that you exactly hit your number are just like minuscule. And so to put another conditional in there and you get equals 0, like return x, this would give you the same result with another conditional and not really all that much faster, because you're never going to hit it on the head exactly. It just doesn't happen. It's like we were talking about pi before, right? Like pi is irrational, and if your beginning 2 points are rational, then you're just never going to get there. You're going to iterate forever, and so you have to decide when the epsilon is, and then that's the whole. So basically, this line does that, I guess you could say, but not as exactly. So, and we're going to use that as an estimate. Now, does it work? Or did I screw up? Oh, well. No, I meant F sign. Oh. Did I put this in the wrong place? C syntax. Yeah. Include math.h? Wow, all this math I've been doing, and I never included math.h. Okay. Does it work? 3.14159. It works. All right. I will take that as proof that our algorithm works. That I didn't screw up in the design of the algorithm, and that it works. So Good. I think we're ready to start take one. Take one. I'm going to record it without... I'm going to practice it without recording first because I know I'll screw up. We'll just go through a dry run here. Maybe I should use doubles for calculating pi just to get a few more digits, because 3.141594, what is the actual value of pi? Nope, this is not what I wanted. What the hell is this? Some random thing in my history. Okay, so it got the last digit wrong. So it's 1.141592. I thought that 4 looked wrong. And it calculated 14159.4. So there's a great example of error. But wait a minute. What was our epsilon? Ah, yeah, we can screw with the epsilon. Let's make the epsilon 0.1. We only care about pi, finding pi within 0.1. Let's see what happens. We get 3.1875. That is within, okay. Now let's do 0.01, see what we get. And now it's 148, so that's a little closer. And let's put a lot of zeros in here and see if that fixes that very last digit. And it doesn't. What? Oh, it hit the assert. After all that talk about not needing the... Let's just raise this. Okay. This might take a while. No. Oh, wow. So what's happening is I made the epsilon so small that it's doing more iterations than I let it do. And it's hitting that assert that I put in the code. And it's still hitting the assert, which surprises me. How many digits do we want? 1, 2, 3, 4, 5, 6, 7, 8. We want all of the digits. So, yeah. Oh, I know why it's not working. Oh my god, guys. Oh my god, you guys. So this is a really good example of when floating point precision can bite you. So what are these two numbers? Bn and An. Bn is where's my mouse? 3.1415925, and Bn is 3.1415924. Okay. So what's the difference? An minus Bn is this tiny small number. Is that less than epsilon? No. Okay, but remember we're subtracting two similar numbers, so that's a no-no. But in this case, I think that's fine. Okay, we add them together, we get x. X is about what it should be. Somewhere around here, we're going to have the exact problem that we discussed in the previous video. We do that. We get hx is a super small number. Hx times ha. Hx and ha are the same thing. Look at that. Hx and ha are the same thing. That's interesting. So they're both positive, so it will go the second branch. And now hx becomes ha, which does nothing because hx was already ha. So let's see. An is 3.1415925, and x is already that. So what's going on here is that the epsilon is smaller than the amount of precision that we have in our floating point number. So I need to do that. It's not crashing. It's taking a while. Yeah, it's still, so I need to do that again. Same problem. Okay. Okay, so we did get that last digit a little bit closer. It was a 4, now it's a 3. That's cool. And 1, 2, 3, 4, 5, 6, 7 units of precision is all that you can get out of this method, which makes sense. We have 7 digits here. And actually, I think it's rounded properly because pi is 2/6, so it should be rounded to a 3. So that's pretty much the most accurate floating point, single precision floating point estimate of pi that you can get. Cool. All right. I'm happy with that. We learned something cool. Actually, now I want to know how many iterations it took to do that. Where does it say that? Thread until 70. Why didn't it tell me? Thread until 70. Oh, I got it. No, I didn't get it. What? Thread until 70 is the line where I return. I don't know how to code. Let's do this. I think the debugger isn't just isn't picking it up. All right. So now we have a little more in there that we can. So run again. Thread until line 70, and it's still not doing it. I don't know why. Okay, this will definitely work. K iterations. Let's see what K is. "19 iterations. Yeah, so no point in that. And because it's logarithmic, remember that log before when we were talking about the how many iterations you would need? Yeah, printf. I don't know why I didn't just immediately do it. Because it's logarithmic, if you want to double your precision, you, like the number of units in precision, you only need to double the, so it would take, like instead of 19 iterations, it would take 19 times 2, 38 iterations. So it's pretty good. Like it, so you get, like each additional digit is a factor of 10 difference, but you only have to do one more iteration to get a factor of something like that. Yeah, 19. Have you read any Stephen King books? The Dark Tower series? 19, if anyone's read that. All right. I think we're ready to go. Our code section is all wrapped up. I'm pretty happy with this. And my strategy is that I'm going to talk about this. going to talk about this, and then use the... Yeah, I've actually only read Stephen King's Dark Tower stuff. But in Dark Tower, 19 is a special number. And I won't explain why, because you'd have to read basically the entire series to understand why, but 19. So I'm going to talk about the Blue Ocean video. And I'm not going to actually... not rendering. Yeah, that was a great demonstration. Like, check out all the objects I'm not rendering. Oh, you can't. That was weird. I wanted to do something like make it so that you could show the frustum in one place, but then actually have the camera and like not lock the camera to the frustum and then move the frustum around. But I don't know, it would have been kind of complicated, and anyway, I didn't. Okay. Let's do a dry run through after I go to the bathroom. I have not seen that talk/book. Let's look it up. Do you have a link? Oh, this looks like it. Oh, this is a GDC talk? Come on, Keynote. Yeah, he's probably about to talk about the exact thing that we just looked at, that we just ran into. Yeah, this is what I covered in the last video. Really? Maybe I should get that book. Okay, I did not talk about this, but it's cool. Well, I mean, we basically learned this. The irregular spacing is the reason, I mean, it's a product of the precision problems that floats have. We did talk about associativity. Yes. These are results of that. Yeah, I've run into this problem before. Right. I see what he's saying. Okay. Yeah, so he's saying that because when you're working with a large number, if you're working with a large number, 1, 2, 3, 4, then if you use an epsilon of 0.000001, then your epsilon will get shifted out. And like you can't hold this and your epsilon at the same time. If you're working with a small number, like we were working with 3, then it works fine. And so like if we were trying to root find to like if here's our whatever, okay, and this value right here is 0.00001. Now we can use an epsilon 0.000000001 and it'll work fine. We couldn't do that because our result was about 3.1. And so we had to go 7 digits out from 3.1 in order to get enough precision. So your epsilon, I guess maybe a way of explaining it is that your epsilon is within the precision that you are, within the floating point precision of whatever floating point you're working with. Thank you for linking that to me. That's a really good point. That's good for me to bring up in my video. So I think I will bring it up in my video. Yeah, and then this is his method for arbitrarily scaling the epsilon based on the values of x and y so that you can avoid that problem. And that's a good idea. We're not going to worry about it here because I can pass in, well, maybe this is what I should just mention, is that I can pass in whatever epsilon I need to pass in. Because I know my result's going to be between 3 and 4, so I know that this epsilon will be a good epsilon for me to do. So that's why you need an epsilon before you start. All right. And that's neat. Yeah. Okay. I'm gonna pee. Pee what there is to pee. Before we get started here. 1 second. I might be pressed for time in this video, and talking about relative tolerance is a good idea, but I have a time budget. We'll see how good my time is. All right. Let's just do a dry run through. with a timer. Okay. Welcome to Math for Game Developers. Let's solve a problem. Did I start the timer? No. Let's say you have the surface of the ocean here and the ground underneath the ocean. And you're trying to render the effect of what happens when rays strike the surface of the water and refract. And this is called caustics. In the part where the wave is concave right here, you're going to get a focusing of waves, of light rays here on the bottom, so it'll be bright. And then where it's convex, it's going to spread out so it won't be bright. Now, in our fragment shader, if you remember from when we did the shading videos, in our fragment shader, we know that when we're trying to render the ground here, we have to pick an individual point on the ground and then determine what color goes to that point. So if I have this point right here, I have to figure out how bright it's going to be. In other words, how many light rays are going to be going to this point. But doing this problem in reverse, where we know what light rate we have, this is why I have to do 20 takes. I can never figure out how to phrase things. If we're doing the problem in the forward direction and we know what light ray we're going to have, then we can tell where it hits the ground, but we're doing the reverse problem. We know what point we want to render, and we have to figure out what light ray goes to that point. And so we're going to do something called root finding. We have a function at h which transforms the an incoming light ray position into an outgoing light ray position. And we want to know, this isn't what root finding is. Root finding is okay, well, I should just say something like, this is the sort of problem that you can solve using root finding. In order to transfer this into a root finding problem is a little bit more involved, but that detail is unimportant. So what is root finding? Just talk about, transition here to talking about root finding in general. Say we have a function, just like this one, and it has some values above 0 and below 0. And we want to find at what x value the function is exactly equal to 0. That's a root finding problem. And we can take this problem and express it in terms of a root finding problem by, I guess I have to do this h function. H of x, let's see. H is an incoming ray of sunlight, and it gets transformed somehow before it hits the ground, and we're trying to find the ground point. So what's the best way to express that this thing is a root finding function? We just have to organize our code so that when this function is equal to 0, then we've struck the point on the ground that we want. That's probably a good way of saying it. And if we can do that, then we've transformed exactly how to do that I don't really want to get into, but if we can do that, then we've transformed the problem into a root finding problem. And so today we're going to look at some methods of finding roots. And the first one to talk about is bisection method. Bisection method actually works really similarly to the binary search that we have covered previously, so I'm going to talk about that. Let's say we have an ordered list of numbers, and we want to know whether 6 is in this list. And we also know that the list is ordered. Well, the first step is we split the list in half, and the middle element is this 5. And we know that 5 is less than 6, so the 6 must be to the right of the 5. And so we have now a new list, just these 3 numbers. And we split the list in half, and we see that the middle element is 6. And we continue splitting the list in half and looking at the middle element, and that's a binary search. So we're basically going to do the same thing. We're going to say, I know that my root is going to be in this range, so I'm going to split that range in half right here, and I'm going to determine whether the root is to the left or the right of this split. It's to the left, so I'll split it in half again, and now it's to the, and so my new range is right here. And then I split it in half again, new color. I split it in half again, and the root is to the right, so my new range is here. And then I keep doing that over and over until I've zeroed in enough into the root that I'm happy. So let's formalize that process. First, what do we need to know? One, we need to know that roots exist. Probably not good. I don't know. I don't need to write down all these things. I'll just talk about them. First, we need to know that roots exist. Okay? If this function is never equal to 0, then we have a problem. 2, we need to know that we have some kind of starting point, A and B, around which we can bracket and inside of which we know that there is a root. So we need that. Third of all, we need to know what's our tolerance, to what degree, to what precision are we happy with finding the answer, the root that we want. Don't know of any better way to put that. What's our tolerance? What's our epsilon? And 4, was there a 4? 4, we need to make sure that there are not multiple roots within our bracket. So we should have a small enough range that we can, a small enough bracket that we know that there's only one root inside the bracket. So now let's go through the steps of the algorithm. 1, we say A1 and B1 are our starting values. So A1 and B1 right here. 2, we calculate X as I'm looking at the reference that I wrote a while ago. A minus 1 plus B n minus 1 over 2. 3. So this is, and that gives us the midpoint. Then we evaluate the function at that midpoint, and we get h of x. But how do we know if the bracket is to the left or to the right? Well, we look at the value at the left of the bracket and the value in the midpoint, and we multiply them together. H of x times h of an. And if the result is less than 0, then we know that one of them must be positive and the other is negative, and so the function must have crossed the x-axis somewhere between a and x. And so if we're less than 0, then our new left-hand point will be the same as the old left-hand point, but the new right-hand point will become x. And otherwise, then the intersection must be on the right side of the midpoint. And so the midpoint will become our new left hand, and the old midpoint will become the new midpoint. And now there's one more step here, which I've completely run out of room to write. I'll have to draw this picture a little bit smaller, I suppose. And that's to decide whether or not we stop this process. And to do that, we see, has the distance between the left and right side of our bracket become less than epsilon, then we stop. Otherwise, if it's bigger than our epsilon, we go back here to step 2 and we start over again. And we continue doing that until we've found within our epsilon, within our accepted error. Okay, so that was pretty good. Let's see how long that took. 15 minutes, 10 minutes. So I can probably get a lot of that more concise, and then, yeah. We'll see how much more concise I can make that. I don't know if it's really realistic that I expect to be able to do these videos in 10 minutes. Like, you can't do math in 10 minutes. Anything worth learning takes a long time to learn, and, you know. I wish I could figure out how to delete a whole section at once. All right. Let's record. No. Yeah. What references, though? I mean, I guess I could link to that talk, but it'd be nice if the talk were on YouTube or something. Just looking at the slides is kind of... Yeah, maybe I will. Okay. What am I doing? I'm recording. Take 1. Welcome back to Math for Game Developers, where today we're starting on our first actual application of numerical analysis. And here's the problem. Let's say this is the ocean surface, and we have some light coming down through the bottom, through the waves. And as the light hits the surface, it's going to be refracted, and it's going to end up bent before it gets to the ocean floor. And so the result is that here in the concave section of the light, we're going to get a very bright area on the floor of the ocean. And here where it's convex, we're going to get a not very bright area. Start over. Freaking love books. Welcome back to Math for Game Developers. Today we are going to do our first numerical analysis algorithm. And here's the problem. Yes, okay, hold on. Let me try this before we start there. Stop before I start in this. Delete. I was trying this before and it didn't freaking work. Select a big area and then, oh, cut. 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 Oh my god, you're awesome. Cut. Oh, so cool. Okay. No, go away. Cut. I'm so happy. Thank you, sir. False chicken. Alright. I didn't try cut. I was looking for a fill tool because I'm so smart. Welcome back to Math for Game Developers. Today we are going to do our first real numerical analysis algorithm. And suppose you have some blue ocean waves and you want to render what the light looks like on the floor of this ocean as it comes in and it gets refracted. It gets bent by the surface of the water. And you're going to get a very light spot here underneath the concave part of the wave, and then a not very light spot right there. But as we learned in our rendering and shaders part of the series that we did before, we have an individual point that we want to render, and we have to figure out how bright it is. So this is like the problem that we had with the rays, but in reverse. We have to figure out what ray hits this point. And there's not always a closed form solution for that sort of problem. So this is one problem of very many that we can use root finding to solve. And now, just as a disclaimer, I don't actually recommend that you do caustics, that's what this is called, with root finding. But this is just an example that we can use to learn what root finding is and how it can be used in many different areas in video games. Not just rendering, but physics as well and a whole bunch of other things. So let's say you have some kind of function here, and you know that it has a root between A and B. Okay? And B. And you want to find where that root is. In other words, at what x value, if this function is h of x, at what x value does h of x equal 0? So that's what we're trying to find out. H of x equals 0. What is x? So we can take this problem that we have up here and transform it into a root finding problem by saying, okay, what position of incoming light strikes this surface, and we have to arrange our formulas such that when the incoming light strikes our surface, then our formula equals 0. And there are a lot of problems that can be turned into root finding problems and solved with root finding techniques. And I'm not going to get into how to transform this one that way. That will come later. For now, let's learn a root finding technique and how we can use it. And the first one we're going to learn is called bisection. Bisection method. Bisection method is really similar to something we've done before, and so I'm going to illustrate that. So if we have 2, 2, 4, we have a list of numbers, 3, 4, 8, 9, 12, 18, 19, for example. And we want to know if 8 is in this list. Let's put 10 in there too, why not? We want to know if 8 is in this list. Then we can do a binary search. And a binary search, if you remember, is we cut the list in half and then we find what is the middle point of the list. And the middle point looks to be about 9. And so now we have a new list that is half the size, and now we find the middle point of that list. And that'll be 3. And then, okay, and we looked on the left side of 9 because we know that 8 is less than 9, and so 8 has to be on the left side of 9 if it's in the list. So now we cut the list again in half, and we see that 3 is less than 8, so 8 must be to the right of 3. And then we continue to do that. We iterate on that until we find either there is an 8 or there's not. And bisection is the same thing. We have this a and b, and we know that right here is the point where h of x equals 0, so I will call that x naught. So let's cut a and b in half and evaluate h of the midpoint between a and b. And then we can see whether the intersection of h and the axis is to the right or to the left. In this case, it's to the right, and so we do the same thing as before. We make this into our new right bracket, and then we consider this interval instead of the whole interval. So we're now only looking at half as much data. And then we'll do it again. We will look at the midpoint. We see that the intersection, the root, this is called the root. Did I mention that? That's why it's called root finding. We're finding the root. So we do another evaluation of h. We see that the intersection between of the x-axis is to the left of our midpoint, and so we cut our interval in half again. And this is called bisection method because every iteration you are bisecting your interval, you're cutting it in two. So there are a few things that you have to know before you can apply bisection method, very important. One, you have to know that the function has a root at all. If h is always positive or always negative, then the function has no root, and you cannot use any root finding methods on it at all. Two, you have to have a good bracket. So you have to know that you can find an a, why is this showing up? An a and a b, such that the a is to the left of the root and the b is to the right of the root. And three, you have to know that that there's only one root inside of your bracket. If there are multiple roots inside your bracket when you start, then you don't know which one you're going to get. But if there's only one root, then you're guaranteed to that root, to get that root. And fourth, you have to know when to stop. That's important. So you have to decide ahead of time a number called epsilon. Epsilon. I'm going to draw, it looks like an E, it's a Greek letter. And you have to determine that when the difference between your brackets is less than epsilon, then you've become acceptably close to the number. So this is the first really important idea in numerical analysis, and it's why numerical analysis is different than most other branches of mathematics. And that's because in numerical, you accept approximations for the numbers that you want to get. And that's why it's okay to work with floating point numbers, because floating point numbers are all approximations anyway. So it's no problem to use them to calculate things. So we're not going to get an exact answer, but we are going to get an answer that is within epsilon of the real answer, and we can make that epsilon pretty small. So now let's look at the steps to actually do this algorithm. So one, we find out what A1 and B1 and epsilon we want to start with. Okay. And then two, we calculate the midpoint. And that is just the mean of A and B. And I say n minus 1 here, by that I mean the A and B of our previous iteration. Okay. 3. Now, so we know what our midpoint is, and now we have to establish whether or not the intersection is to the left or to the right of the midpoint. How are we going to do that? Well, when we originally cut this function in half, light blue, we evaluated the function at the midpoint. And now we're going to do a little trick. We're going to say h of x times h of a. And in this case, we see that h of x is positive and h of a is positive. And so if there's no intersection between a and x, then they'll both be positive. And so there will be no intersection to the left of, so then we know that the intersection has to be to the right. Otherwise, if it's negative, then the intersection has to be to the left. And so that's what we're going to use to figure out. So if it's less than 0, that means the intersection has to be to the left, which is not what's in this picture. But then the left bracket will remain the same, and we will, for the next right bracket, we will use the current midpoint. Otherwise, the left bracket will become the current midpoint, and the right bracket will stay what it was before. And then the final step in our algorithm is to test whether or not we've gotten within epsilon of the number that we want. And this is how we do that. If the difference between our bracket is bigger than the epsilon, and if this distance right here is bigger than epsilon, then we'll go back to the beginning and we'll find a new midpoint. Otherwise, if it's less than epsilon, then the distance from the bracket to the root must also be less than epsilon, and so we're done. So step 5, the last step, is to return one of the brackets. It doesn't really matter which one. So that's bisection method, and we're going to go to the code section of the video now to code it up, and we're going to see it at work in an actual, not a game this time, just a demo. So I'll see you there. All right, guys, that was not bad. Let's save that in Bisection. Untitled as everything is these days. That was, oh my God, I took 11 minutes to explain that. That's ridiculous. Should I even do a code section at this point? I said I would, so I should. So the question is always, what do I delete and write while people are watching? Thank you, Simon. I didn't mess up too bad. I think I should delete this. I'll put it back though, and see, you guys are about to watch me cheat. Cha-ching! I took a screenshot. This is how I cheat. I open the screenshot of what I just wrote, and I put it on my other monitor. And then while I'm writing the code, I just copy it. And that helps prevent me from making mistakes, which I didn't make mistakes the first time. So I don't know why I'm so worried about it, but just in case. So let's start the code section. Let me make sure I have this open. Yeah. Okay. Okay. This is going to be a much longer video than 10 minutes, but let's do it. make it the whole screen. And start recording. And thanks for joining me in the code section. I'll explain where we have so far. We're going to use bisection method to find the value of pi as was suggested by somebody on Twitch, on the stream that I'm streaming right now. And our left bracket is going to be 3 and our right bracket is going to be 4. As you know, pi is between 3 and 4. And we're going to use as our function sine, because sine of pi is 0. And so that is a perfect example of a root finding function. We're finding the value at which sine is 0, and that is pi exactly. Very convenient for us. And then we have to decide on an epsilon, and we're going to use 0.000001, which works in this case. Depending on your case, you may have to use a different value, and you should not just use 0.000001. You should use something that works for your situation. And also suggested by the streaming audience, I have a link in the description to something that you can go to read a little bit more about that. So, but for now, let's take a look at the bisection method that we're going to use here. Okay, so this function up here is the bisection method. We have our initial a and b, and the function we're going to evaluate, and the epsilon. That's all the stuff that we needed to start bisection method. So we're going to make our current an. We're going to initialize it with a1 and b1. And then we're going to evaluate h at a and h at b. Okay, so ha is the value of h at a, and hb is the value of h at b. Let's make this h. That's d. H. Okay. So let's start writing our... We start with step 2, which is finding the midpoint, and then we test the midpoint, h of x. Step 3 is it less than 0? If it is less than 0, then we're going to update the right bracket. So if it's less than 0, that means our intersection is on the right. So we're going to update the right bracket to be the midpoint. And we're going to update the evaluation at the right bracket to be the evaluation at the midpoint. Otherwise, we are going to move the left bracket to be the midpoint, and the left bracket, and update the evaluation at the right bracket. Okay, and that should be all we need. Let's compile it and run it and see what we get. We got 3.141593, which is very close to the actual value of pi is 3.1415926. So when it's rounded, that is correct. Now let's make our epsilon a little bit smaller and see what the algorithm does. So say we want to find, in fact, let me also do this. We'll find how many iterations it takes to come up with the answer. We're going to print that out real quick. So with our original epsilon, it took 19 iterations. So now let's reduce it to 0.01 and see what answer it gives us and see how many iterations that took. It gives us now 3.148, which is pretty close. 3.1415 is the correct answer, so it is within 0.01, but it took fewer iterations, so it did it a little bit faster. So Great. Next week we are going to... Oh, and here we go. I'm going to give you the finished result here. This is a program that I wrote a few months ago. And you can see the caustics on the floor, which I simulated in real time. Again, not the best way to do caustics. It's really slow. But I wanted to do a little bit of root finding, and you can see that it worked. So this is the sort of thing that you can do with a root finding technique. And in this video, actually, I use a lot of other numerical analysis techniques that I will cover in this series. We're going to see a lot of the stuff that I did to make this series. So, and we will see that next time when we cover... What are we covering next time? What are we covering next time? Oh yes, fixed point iteration. See you then. All right, guys. Oh, thank you, Chromelick. Yeah, I mean, if you watch the streams, then you pretty much don't need to watch the actual videos, I suppose. I think I am going to do this every weekend. And maybe stream some of the other stuff I've been working on, too. I don't know. Just as a little teaser, if you've seen my talk, which you probably haven't because I didn't post it to my YouTube, but I did a talk in November, which was an introduction to linear algebra, which is nothing you don't know if you've been watching my videos. But I did it in kind of a cool way. It was like an interactive web page that people could play with as I did the talk. And I think that's really cool. So I want to transition from doing videos that are kind of static Khan Academy style videos to interactive web pages that are still me talking and writing like what I do, writing what I'm saying. So it would come across just like one of my regular videos, except it would be interactive because it would be a web page and you can kind of interact with it. You can interact with it, but that requires a little bit of coding that I've not done. So that's one of my new projects. And if you were present earlier in the, I'll link it. And if you were present earlier in the stream, then we looked really quick at another game that I'm working on as well. So November, this should get me there. So I don't know, I might do some coding, but just straight coding isn't as interesting as...
That probably does have a definition, but let's just look at it as a...
Just straight coding isn't as interesting as like the actual developing of math that we do. So I might not do as much streaming of that, but we'll see. All of these things can be streamed. All right, come on. So let's see. Come on. There we go. So that is a 17-minute video. Killing me here. But it's good. I think it was a really good take. So I'm happy with both of them, and even if it's 18 minutes, I think it's the title and game of the stream. How do I do that? Ugh. I don't even know how to do it. Really? Dashboard. Aren't I on the dashboard? Wait, what did that say? Oh, lame. Where's the dashboard? Dashboard. Dashboard. Oh, title of this broadcast. But I'm almost done with the broadcast. Untitled forever. I am not playing. I don't understand this. Okay. Well, I'll do that later. Maybe next stream. What is this playing? Playing? I'm playing. Oh, I'm playing a game. I'm playing. I'm not playing. All right. Done. Yeah, whatever. Okay, so all that's left to do is editing, and then I will go eat dinner. And editing is kind of boring, but actually this take was pretty good. I don't really know if I need to edit that much.
One of the brackets. It doesn't really matter which one. So that's bisection method, and we're going to go to the code section of the video now to code it up, and we're going to see it at work in an actual, not a game this time, just a demo. So I'll see you there.
I could put playing math. Playing with math. Math at play.
Oh yes, fixed point iteration. See you then.
All right. It's pretty much a wrap on that one. Oh, actually, you know what I want to do though? I want to put an overlay of the Blue Ocean video. Here it is. While the video is initially playing, so open location. No, oh, come on. Tell me its location, please. Where on my hard drive is this file? Please tell me. There it is, Dropbox public. In my Dropbox, public, Blue Ocean, Blue Ocean. And then we'll just put that there. Command enter, thank you. I am so bad at computers. And we'll fade that in and fade it out and move it to the top right here. See how that looks.
And suppose you have some blue ocean waves and you want to render what the light looks like on the floor of this ocean as it comes in and it gets refracted.
Yeah, I'll start it when I start talking about the floor of the ocean.
Render what the light looks like on the floor of this ocean as it comes in and it gets refracted. It gets bent by the surface of the water. And you're going to get a very light spot here underneath the concave part of the wave, and then a not very light spot right there. But as we learned in our rendering and shape...
Alright. That's pretty much it for this video. So wait, what was I command entering? I want to see that again. Command enter here? No, it just plays it. Oh, I didn't want to play it. I want to figure out where the video is. Like where the file is on my hard drive. But I found it. Okay. So this will take like half an hour to render. Let's get it started. Oh, really? Oh, in the search? Nice. I'm still learning, Max. Thank you. So render. And I'm rendering these in the wrong order, but that's fine. Okay. Well, rendering is not terribly interesting, and I'm hungry. So I am gonna go eat something, I think, and end the stream. Thank you everybody who tuned in. I really appreciate it that people came out to watch me fumble with words, and I really enjoyed myself, and I guess you guys did too. It looks like it. I'm planning on doing this every week, I think, every weekend, except next week I think I'm going to do it on Saturday and a little bit later, maybe 1 o'clock, to help the Aussies tune in. So, thank you guys very much. Love you lots. See you next week. Unless I do it, I might do an interim stream of me just coding. So.